I went through all these reasons. We went through the reasons of why we give oxygen, treat hypoxemia, decrease the work of breathing, and to decrease the work of the heart. Then we talked about some of the hazards. Once we decided to give oxygen, there are some hazards involved. One hazard is oxygen toxicity, which has to have two things, increased FiO2 and time. Then you have absorption atelectasis, is when you have high FiO2 and obstruction. And what happens is that the obstruction the oxygen is continuing to filter into the alveoli, but the nitrogen is washed out. Once the nitrogen is washed out, then the alveolar falls below critical volume and collapses, because we said that nitrogen is the strong workhorse, right? It's the one that exerts the most pressure because it's 78% of the atmosphere and 78% of the space in the alveoli, which exerts like 500 and something, I think 592 millimeters of mercury of pressure inside the alveoli. Therefore, when that nitrogen is gone, the alveolar walls can't stay open, so they collapse. And so that's absorption atelectasis, okay? And then O2-induced hypoventilation. Then that was for our COPD patients or our chronic hypercarbic patients. Our patients, our chronic hypercarbic patients who have high levels of CO2, they no longer have their central chemoreceptors in play. They no longer have those in place. So therefore, they only live off of their peripheral chemoreceptors. And since their peripheral chemoreceptors respond to hypoxemia to tell them to breathe, then you always want your COPD patient or your chronically hypercarbic patient to have a mild hypoxia. If they don't have hypoxia, the body is not going to breathe. And so therefore, if you give them too much oxygen, then you knock out their hypoxic drive. They're not hypoxic anymore. And so they no longer have something there that's reminding them to breathe, okay? They live only through their peripheral chemoreceptors. And you knock that out when you give them too much oxygen. So that will be oxygen-induced hypoventilation. They start breathing slower, and that CO2 is increasingly going up, because they're hypoventilating. And they end up going into respiratory failure because you gave them too much oxygen. All right. Then we talked about RLF and ROP, which was retrolineal fibroplasia or retinopathy of prematurity, simply when given higher PaO2s greater than 80 millimeters of mercury for an extended period of time can cause the vasoconstriction in the retina, okay? That vasoconstriction restricts the blood from flowing to the blood vessels. So that's necrosis, right? Ischemia, which leads to necrosis of the blood vessels. When those blood vessels die, the body tries to make new vessels, but they're so quickly made that they hemorrhage, which means bleed, and that blood causes scarring in the retina, leading to blindness, okay? So you have to make sure that your child or the baby that you're taking care of, his PaO2 is not greater than 80 millimeters of mercury, all right? And this is mainly susceptible to infants up to a month. After about a month, this is not a problem, okay? Usually we're talking about our firstborn babies or our premature babies. All right, the guidelines of O2 we talked about: don't ever hold oxygen back from somebody just because he has COPD. Oh, you got COPD, so I can't give you no oxygen, right? Don't ever do that. Also, oxygen concentrations that are less than 40% are rarely to ever cause toxicity, all right? 100% oxygen has not been shown to cause toxicity when you lose it less than 24 hours. But when you get past 24 hours, we start having a problem, okay? Oxygen is not contraindicated for brief periods of emergency. If it's an emergency, give it to him. I don't care if he smoked 30 packs a day. If he's in an emergency and his oxygen level is down in the 70s, give him some oxygen, okay? Give it to him. Shapiro always said to allow a patient to be exposed to dangerous levels of hypoxia for fear of oxygen toxicity is intolerable, all right? Intolerable. Don't ever do that. Always use minimal oxygen concentrations to achieve a state of no hypoxemia or no hypoxia. Use minimal. Always go into your tube bag and try to use the minimal, okay? If 2 liters per minute will work, then use 2 liters. If that don't work, you go up, right? We go up from the nasal cannula. You're going to learn today about the different flow systems. We have a low flow systems that we can use, and if they don't work, we go into our high flow systems, okay? But start low and try to, because oxygen is a drug, and they can get addicted to it. So you don't want to give them a whole lot. It's harder to get them off, okay? And always monitor the patients carefully. All right, so low flow systems is where we are today. And there's some indications for low flow systems. Who can qualify or who will benefit from a low flow system, all right? The patients who have tidal volume between 300 and 700 milliliters, respiratory rate lower than 25, and a consistent ventilatory pattern. They must have these 3 things in order for them to qualify for a low flow system, okay? They have to have a tidal volume between 300 and 700, which is normal, right? Normal tidal volume, normal respiratory rate, and a consistent ventilatory pattern. That means they're not breathing shallow and shallow, and then real deep, and or real deep and then shallow. It's got to be consistent, regular, consistent, like you're sitting here breathing right now. You will qualify for a low flow system. Those are the 3 indications for a low flow system. If they don't qualify for low flow, then you give them a high flow system. Simple as that. All right. So indications for low flow systems are there. All right. Low flow systems. There's some key information we need to know about low flow systems. Very key information. Hold on one second. I need to pause this for one. All right. So low flow systems will consist of a few different devices, which we'll talk about today. We already said what the qualifications or the indications of low flow systems are. But you need to understand that the reason why you have to have a consistent ventilatory pattern is because of air entrainment, okay? Air entrainment. So you need to write that down somewhere. Air entrainment. E-N-T-R-A-I-N-M-E-N-T, entrainment. E-N-T, look at C on your PowerPoint, on your screen. See? Air entrainment. Air entrainment's concept is that oxygen that's coming from the wall or from the flow meter is 100% oxygen, okay? Oxygen that is coming from the wall is 100% oxygen. Oxygen coming from an oxygen cylinder is 100% oxygen, okay? And so when I hook this up to an oxygen cylinder, the oxygen that's coming out of the nares is 100% oxygen. The reason why it goes down is because when you inhale, you suck in outside air around it, and that bleeds it down to a certain amount, okay? You think of it like Kool-Aid and water. If I have a pack of Kool-Aid and I put 2 drops of water in there, what's the concentration of the Kool-Aid gonna be? Watery. I said if I put a pack of Kool-Aid in a pitcher and put 2 drops of water, it's gonna be real high concentrated Kool-Aid, right? But if I put 5 gallons of water on 1 pack of Kool-Aid, that's gonna drown the Kool-Aid to almost nothing, right? So that's what's happening with outside air. When we entrain outside air mixed with the oxygen, it bleeds it down, okay? It makes it go down, the concentration go down. I also use this analogy that some people laugh at. When your spouse, y'all riding in the car, and your spouse farts in the car, and the windows are up. Well, the concentration of the fart is extreme, right? What's the first thing you do? Let the window down. Why do you do that? So it's not really that it's letting it out, but it's air entraining in. It's sucking in from the window, then it bleeds that smell down, okay? And so the more air you entrain in, the less the FiO2 will be. The FiO2 is the fraction of inspired oxygen, right? How much oxygen is coming out of those binasal cannula, right? If it's just nobody on it, it's coming out. That's 100% coming out. But when I put it in my nose and I breathe in, I'm sucking air around it through my nose as well. And that bleeds the percentage down, okay? And so what they have a rule of thumb, a low flow device can never guarantee an FiO2. That's a major thing. Write that down as well. The FiO2 is not guaranteed in a low flow device. That's one of the key aspects of low flow devices. You cannot guarantee an FiO2. You just can't. I can on a high flow system. So if I need a definite FiO2, then I'm gonna put them on a high flow system. That way I don't care how they breathe. He's gonna get this percent that I set, period. Okay? But if they're on a low flow device, I cannot guarantee the FiO2 because of the air entrainment around the patient's nose. They may breathe faster or deeper, and that FiO2 will vary, okay? But we can estimate the FiO2 by using the rule of fours, which we'll get to in a minute. But I just want you to understand this case of air entrainment. When I put that nasal cannula into my nose, you see all the rest of the space I got in my nose, right? All of that space is sucking in outside air. And so that 100% oxygen is going down. It mixes with the outside air and the percentage or the strength of it goes down, okay? And so that's what we're getting ready to learn. The deeper I breathe, the lower the FiO2. The more shallow I breathe, the higher the FiO2. Because if I'm breathing like this 12 times a minute, right, regular, consistent pattern, then I'm going to get whatever we estimate it to be on, depending on the liters that I have it on, okay? But if I slow my breathing down and only breathe 2 times a minute, well, then that oxygen is constantly pouring and it's collecting in my anatomical reservoir, right to the back of my nasal pharynx. So when I do take a breath, that's pure oxygen going down, okay? But when I breathe normal, in, out, in, out, in, and out, consistent, regular tidal volume, then it's going to entrain just the amount of air to get me down to what I say that I'm on, okay? And you'll learn those, what I'm talking about in a minute. I just want you to get to understand the concept of air entrainment, okay? Air entrainment. So the factors that influence, and look at A says FiO2 will vary according to the patient's ventilatory pattern, okay? It's going to vary. If it's normal and consistent, then it may hang around what we estimate it to be, but we can't guarantee that, all right? What are the factors that influence the FiO2? Well, the patient's ventilatory pattern. You're going to hear me say that all the time. The ventilatory pattern, which is the respiratory rate, the IE ratio, and the tidal volume. Those are what we're talking about, okay? That's one thing that influences FiO2. The flow that the gas is on will influence the FiO2. How much liters do I have it on? How much? 2 liters? Do I have them on 6 liters, right? 3 liters? Reservoir size. Now, you have a system reservoir and you have an anatomical reservoir. That anatomical reservoir is your nasal pharynx, right? Or your oral pharynx, the space up in your inside of your body that's housing the gas in between breaths. If I'm breathing regular, then it doesn't have time to get real strong. But if I slow my breaths down to like 3 times a minute, then it's constantly pouring. And so by the time I do take a breath, all of that reservoir space is pure oxygen. So that's what makes it vary, okay? If you have a patient that you're not sure how they're going to breathe, or you want them to have a definite FiO2, then they must be on a high flow system. All right, they'll be on a high flow system. All right, so let's look at C. As the tidal volume increases, the FiO2 will decrease, just like the fart in the window. As the volume of the air in the car increases, then the smell will decrease, okay? As the tidal volume decreases, then the FiO2 will increase. If the fart is there and you let the window up, it's going to get stronger because you have decreased the flow, right? You decreased the volume that's in the car. Okay, so if I breathe, say I'm breathing at regular tidal volume, 300 to 700, let's say 500, right? If I instantly go up to 1,000 liters a minute, right, and I'm just pulling in 1,000 liters, then my FiO2 is gonna go down because I'm pulling in more outside air, okay? If I'm breathing 500 and then if something happens and I go down to 100 liters per minute, right? Just 100 tidal volume. Well, then that means now the FiO2 is getting higher and higher because I don't have as much outside air bleeding it down, okay? So look at C, it says as the tidal volume increases, as the patient's tidal volume increases, the FiO2 decreases due to more entrainment of room air. As the tidal volume decreases, the FiO2 will increase due to less entrainment of room air, okay? And as same thing with the rate. If the respiratory rate increases, then the tidal volume will decrease due to less time for the reservoir to fill up. So that reservoir in your oral pharynx, this right here, as this nasal cannula is on the patient, right? If the nasal cannula is on the patient, okay, and he's breathing 3 times a minute, well then as this air is filling up, all this oxygen is just sitting right here, right? It's constantly coming out because it's constantly coming out of the nasal cannula, right? And so as that's doing that, this is the reservoir, the nasal pharynx and the oral pharynx. This is an anatomical reservoir. This gas is just sitting here waiting on you to take a breath. And you finally take a breath, all that goes down. That's a high percentage of FiO2. But if you are breathing normally, it doesn't have time to collect. It's going in and out, in and out. It doesn't have time. So the respiratory rates will affect the FiO2 based on the time. Okay. If I start to breathe faster, FiO2 will decrease because it ain't had time to build up. Okay. If I start breathing slower, then the FiO2 will increase because I have more time for that FiO2 to build up in the oral pharynx. Okay. Key thing here again is FiO2 is what? Unpredictable with a low flow system. With a low flow system is unpredictable. We can guess, but we cannot guarantee it. Okay. For the most part, it's immeasurable. It may vary from minute to minute depending on the ventilatory pattern. If the patient starts breathing real deep, it's gonna go down. FiO2 gonna go down. If he starts breathing real shallow and slow, it's gonna start breathing up because it's constantly coming out. Okay. These are some of the low flow devices here. This is the nasal cannula, right? Low flow devices. This is a nasal cannula right here. Same thing I've been showing you, nasal cannula. Then you have a simple face mask. This is called a simple face mask, simple O2 mask. Okay, let me get my pointer out. This is a simple O2 mask, also known as a simple face mask, right? Notice it has a mask and a small bore tubing. Notice how the nasal cannula is all small bore tubing, right? The anatomical reservoir is inside of you, but this one has a system reservoir, which is in the mask, okay? In the mask, it collects as well. That's considered a reservoir because that's anywhere where gas can collect is considered a reservoir, okay?
More accurate than the cannula.
No, they're all low flow systems. They're all you cannot guarantee the FiO2 on any low flow system. The only reason we go from a cannula to a simple face mask is if the cannula is not enough. If I have them on the cannula, you're going to learn it only goes to a certain liter flow. Then you have to switch over to the simple mask. And if that don't work, we go into the non-rebreather and the partial rebreather mask. Okay? So, and you're going to learn what the liter flows are. So I think and they overlap a little bit. Now, the nasal cannula can go up to like 6 liters per minute. After 6 liters per minute, you don't need to try to go 9 and 10 on a nasal cannula. If 6 liters per minute on the nasal cannula is not getting it, then we'll go to the simple face mask, which is 5 to 8 liters per minute. Okay? The simple face mask is 5 to 8 liters per minute. Okay? And then the partial and non-rebreathers are 8 to 10 liters per minute. All right, so you make sure you're writing this down because there's a test questions. The liters per minute on the simple face mask is 5 to 8. 5 to 8 liters per minute. It has to be at least 5 to prevent the buildup of what? If you're looking at this mask, what will build up if my liter flow is not enough?
CO2.
CO2, good. So if my simple face mask is not at least 5 liters, say you try to put them on a simple face mask at 2 liters per minute, that ain't gonna work, because as they exhale, the CO2 is building up in the system reservoir or the mask. Okay, so it has to be at least 5 to flush out the CO2. Okay.
What do you say it has to be for the was it non?
Yeah, I'm getting to these now.
Okay.
So then if the simple face mask is not enough to keep your patient sats up or whatever, then we can determine either going to a partial rebreather mask and a non-rebreather mask, okay? This picture here on the side is a non-rebreather mask. That means you cannot rebreathe your own gas. The patient is not rebreathing their own gas. 100% of the gas is coming from the device, okay? So that gives them a high FiO2, like almost 100%. This is the type of mask you put on a patient who's coming in from a house fire, right? Because we know that in a house fire, what do we expect to be happening? Carbon monoxide. Hold on one second, I'm gonna get one of those devices. All right, I showed you the nasal cannula. Stop the share. This is a nasal cannula. It's like this. I showed you, it goes on the patient, in the nose, behind the ears, and then it pulls up like that. This is a nasal cannula, okay? Low flow device. Then let's look for the simple O2 mask. This is a simple O2 mask. I cut the tubing off because I ain't all that extra tubing on. Notice you have the mask, which is a reservoir, right? It's got some holes for exhalation so the patient can easily exhale through there. And then you have the flow coming from a small bore tubing. This is a simple O2 mask, okay? The liters per minute for O2, simple O2 mask is how much? 5 to 8 liters per minute. It must be at least 5 to wash out the CO2. Otherwise, you'll start to build up CO2 in the reservoir on a patient, okay? All right, so that's the simple O2 mask. Then we have our rebreathers. Let me take one of these things off the other one for teaching's sake. This is a non-rebreather mask. This is a notice it has a reservoir bag, okay? And there's a difference, they're really close, but there's a difference between the partial rebreather and the non-rebreather. The non-rebreather mask has a one-way valve on the inside. See that? It raises up for the gas to come up to the patient, but when you exhale, your exhale cannot go back into the bag, okay? You cannot rebreathe your own gas. So it's a non-rebreather, okay? It has a one-way valve right here. See that valve? There's a valve right here that goes up when the oxygen is coming in. When I breathe it in, I can suck in. When I breathe in, I'm sucking all the oxygen out of the bag. This bag will be inflated, okay? I'll be sucking all the oxygen out of the bag, right? But when I exhale, I cannot exhale back into the bag. Got it? When I exhale, it goes out the side. See these flaps here? Look at these. So when I blow out, these open up to let me exhale, but when I suck in, they close. So I don't suck any outside air in. I'm only sucking what? Oxygen. I cannot rebreathe my own gas, and when I inhale, these continue to close, and all that I can inhale comes from this bag, pure oxygen, okay? Now, there's a trick to the non-rebreather, because when you get it, they usually take one of these off. It's still a non-rebreather because it has this valve here, okay? But the reason they do that is because what if it becomes disconnected from the oxygen and you didn't know it? And now the patient is sealed on the patient's face. When he try to inhale, if you have this on there, he can't inhale no more. There's no more oxygen. The bag is flat because it came loose, right? You didn't know, you busy. It came loose, or he pulled it off, or somebody did something. And now when he tries to inhale, he's going to suffocate, right? Because these flaps are keeping him from sucking in. So they usually, when you buy them, they come together like this, but the manufacturer or the respiratory department will pull one off, okay? So for safety, okay? It's simply for safety. Just in case it gets disconnected, then you don't have to worry about it. They might not be getting no oxygen, but at least they're able to suck in some kind of air they can breathe, okay? So this is taken off for safety, all right? But I put it on for teaching because when you buy it, it comes like this, okay? You got a flap on both sides. Both exhalation ports have a valve. Also, the bag has a valve. This is a non-rebreather. All right, now let's look at the partial rebreather. Partial rebreather. To make one. All right, this will be a partial rebreather. Notice that the partial rebreather also has a reservoir bag, but does it have a valve in here? Huh? There's no valve. That's open, right? No valve between the mask and the bag. No valves on the sides, okay? This makes this a partial rebreather mask. That means when I'm breathing, when I exhale, partial amount of my gas goes back into the bag. And when I inhale, that same amount that I just inhaled into the bag comes back to me. So I'm partially rebreathing my own gas, okay? So that is a partial rebreather mask, okay? And the main thing is it doesn't have a valve between the mask and the bag. The partial rebreather does not have a valve between the mask and the bag. It's open, okay? It also does not have valves on the exhalation ports of the mask. But the non-rebreather mask does have one-way valves on the exhalation port, and it also has a one-way valve between the mask and the bag, okay? That's a non-rebreather mask, okay? Now, the flow leader for a non-rebreather or a partial rebreather is 8 to 10 liters per minute. 8 to 10 liters per minute. What's the liter flow for the simple face mask?
5 to 8.
5 to 8. And the nasal cannula is usually at 1 to 6 liters. We usually hardly ever go that high. We usually do 4 or 5 liters. If that ain't working, we go on to something else. Okay? So let's look at it in action. I'll use an E-cylinder to show you the non-rebreather bag, because there's something important about the non-rebreather as well. If the patient is on a non-rebreather and the bag collapses every time he inhales, you need to increase the what? Flow. So it might be on 10 liters, but if he's breathing that hard and the bag is collapsing, crank it up more, okay? No matter what, if the bag collapses on inspiration, make sure you write that down. If the bag collapses on inspiration of the non-rebreather or the partial rebreather, you increase the flow. As simple as that. All right. Put the flow ring on here. All right, so it's 8:50. Go ahead and take your break, 10-minute break. And I'm gonna set this up so when you come back, I'll show you the bag, what it looks like, what it sounds like, and we'll move on. Okay, we're back from break, and I'm about to show you this right quick, and we're gonna move on. This is a non-rebreather again. We said a non-rebreather has one-way valves on the exhalation ports of the mask. It also has a one-way valve in here between the mask and the reservoir bag. The liter flow for the non-rebreather and the partial rebreather are both 8 to 10 liters, okay? Unless the patient's bag totally deflates on inspiration. If that happens, then you increase the flow. If you get a question, see how the bag is open? It's now, you can hear it. It is now full, right? This is how they use it. As I exhale, gas comes out. My exhale gas can come out of the mask, but it doesn't go down into the bag. So I'm not able to rebreathe my own gas. That's why it's a non-rebreather. Now, if I'm inhaling this and the bag flattens every time I inhale, it just goes flat, then you increase the flow. That's going to be a question. What do you do if the bag deflates during inspiration on a non-rebreather or partial breather? The quick answer is increase the flow. Okay? Simple as that. All right. So make sure you understand the difference between the non-rebreather and the partial rebreather. And we're going to get into those liter flows and, you know, how much FiO2 in the PowerPoint. Okay? So those are a couple of the low flow devices. There are going to be a couple extra that are mentioned that you're going to hardly ever see in your whole career. All right, but you still need to know them. Okay? All right, so what are some of the low flow devices in particular? The nasal cannula, also known as nasal prongs, it has some advantages and some disadvantages. Okay? Some of the advantages are it's economical, comfortable, and the patient is able to eat, cough, and talk, right? If they have the nasal cannula on, they can eat, they can cough, they can talk, right? Move around. That's some of the advantages. Also very cheap, right? And it can be made to be comfortable, all right? It doesn't have something big mask sitting on your face. Some people are very claustrophobic and can't have a mask on their face, okay? Some of the disadvantages, like any other low flow devices, is imprecise FiO2. It's not precise. FiO2 is not precise, okay? And so another thing is disadvantage, it can dry the nasal mucosa because medical O2 is very, very dry, okay? So it can dry you up real bad, especially after about 3 or 4 liters. You need to put on some humidification, right? You'll learn that a little later, but there's a little bubble of water that can call a bubble humidifier that you can hook up to a nasal cannula, and it moistens the gas a little bit, okay? Because it makes it very, very dry. It can make your nose bleed and crack, all of that. So they have to be very careful because it is very, very dry. Now, the flow ranges of the nasal cannula. The flow ranges up to 6 liters per minute. Flows greater than 6 liters per minute do not significantly increase the FiO2 due to anatomic field reservoir. So they saying after 6 liters, you need to switch. It's just, if you put them 10 liters per minute on the nasal cannula is no different than 6, right? It's just at that point, you need to move on to the next device, okay? So the flow ranges of the nasal cannula is up to about 6 liters per minute. Now, I told you that they overlap, okay? They overlap. So let's look at what's else out here. FiO2. Now, remember we said it's not precise, but it's variable depending on what? The patient's ventilatory pattern. If they breathe in deeper, the FiO2 goes down. If they breathe shallow, then FiO2 creeps up, okay? Because you're not moving a lot of outside air, entrainment, all right? All right, but we can guesstimate it by using the rules of 4. The rules of 4s. So 0%, well, let's just say, atmospheric oxygen is 20.9%, right? And we round up to 21%. But if we use 20.94%, if we add 1 liter of oxygen, it goes up by 4%. 2 liters, 4 more. 3 liters, 4 more, okay? So if room air is 20.95%, they're saying if we put them on 1 liter of oxygen, their FiO2 will be about 24%. Look at the paper, the PowerPoint. Oh, okay. Because I want you to see these lists. If they're on 2 liters, it goes up 4 more percent. So 2 liters on a nasal cannula is about 28% FiO2. 3 liters is about 32%. 4 liters is about 36%. 5 liters is about 40%. And 6 liters about 44%. Okay? That's called the rules of 4 to estimate the FiO2, as long as they have a persistent or consistent ventilatory pattern. Okay, so if I have a patient on 2 liters, that we can estimate the FiO2 to be about what? 28%. Okay, if the doctor says I want them to get about, he's not being precise, but if he say I just want them to get about 40% oxygen, and we're using a nasal cannula, how many liters would you put them on? 5 liters. Okay, that's how that works. Okay. Then it says most studies indicate that mouth breathing does not significantly affect the O2 delivery, because a lot of times they say, well, you got the nasal cannula in, but he's sleeping. He sleeps with his mouth open, so he's still getting pushed into that oral pharynx. Okay, it may go down a little bit because he's mouth breathing, but not significant. Okay, it's not significant. Huh? Doesn't matter if he's breathing through his mouth. He's a mouth breather. He's still getting that flow through the pharynx. All right. Here's the rule of 4 again, and it's going all the way up to 10 liters, but don't worry about it. After 6, we stop looking at it. Okay, it's just a picture I put in there. Rule of 4s. Don't forget that. Now, another layer, the next low-flow device that you didn't have is called the nasal catheter. Nasal catheter, right? And it's similar FiO2s and indications as the nasal cannula, but this one is inserted using a water, some KY jelly. Okay, we use KY jelly a lot in the for the nasal catheters to moisten it up before we suction a patient or anything. Okay, but what it is a one tubing. Right, it kind of looks just like this. It's just a one tube with a couple of holes on the end, and what happens is they will put some KY jelly over it and then insert it up in the nose, down, it says just to above the oral pharynx. You should see it below the uvula and then pull back. Okay, so you put this in their nose and push it in. Tell them to open their mouth. What's the uvula? Yeah, the little piece of meat that's hanging back there, that's the uvula. So the nasal catheter would be inserted until you see it come down past the uvula in their mouth. Then you will, once you see that, you'll pull back just a little bit so you can't see it, and then you would tape it to their face. Okay, you would tape it to their lip, okay, to stay in there. That's a nasal catheter. That's why I say you don't hardly ever see. We haven't ever use that anymore, okay? But it's good because the oxygen that you use is less because it's way down here. Ain't no much air entrainment way down there, okay? You're not sucking in a whole lot. It's all the way in, and the holes are at the end of the catheter, so the oxygen is getting poured right in to the lower airways, okay? But like I said, you don't hardly ever see it, but you need to know that the nasal catheter, how you insert it, okay, and it must be changed how often? Every 8 hours, and you have to rotate the what? The nair. So after 8 hours, you take it out, put it in the other nair. 8 hours, take it out, put it in the other nair. Must be changed every 8 hours and rotate the nairs, okay? Rotate the nairs. Rarely used. You're going to be doing a lot of that when you're suctioning patient. Sometimes you have to suction NT suction, which is nasal tracheal. So you have to go in the nose and go and past the uvula down into the trachea and then suck that stuff out. Because if they can't cough it up, you can hear them rattle. The mouth, no. And if they don't have a trach, yeah, if you got a trach, you use the trach. But if they don't have a trach, like if you get sick and you get weak and you can't cough that stuff up, if I don't get it out, you're going to get pneumonia and die. I have to get it up. That's why cough is so important, that the patient able to produce a cough, because that's what protects the what? Airway. When you inhale some water, you eating some chips, and one of them chips just act like they want to get close to that airway. What's going to happen? Coughing super hard, eyes watering, everything, because the body would not accept nothing but gas in the airway. All right? So when you start building up mucus and infectious mucus, when it starts getting toward the airway, the body trying to get it up, but if you're weak because of the illness, that's all you can do, right? And if you can hear it gargling now, you can hear their sats will start dropping, and if they get it in the airway, then that's aspiration pneumonia. You're just getting sicker and sicker. So we have to take a nasal catheter, not a nasal catheter, but a suction catheter, and wet it up with the lubricant and go down to your trachea and suck that stuff up, and it'll just be flowing, right? You'll feel so much better when they get it up for you because you couldn't get it up, all right? So that's something that you as a respiratory therapist have to do. All right, so that's the nasal catheter. Similar indications for the nasal cannula. All right, simple O2 mask, what I just showed you, the simple O2 mask, this one here. Notice it does not have a bag. It's a mask with the small bore tubing. Okay, mask with the small bore tubing. Okay, was that you or me? All right, so this is the simple O. Now they're saying FiO2 is about 35 to 55%. That's about what they're going to get when you use the 5 to 8 liters. Okay, moderate concentration. See, if I need a little bit more moderate concentrations, I can use this instead of that nasal cannula. Depends also on the ventilatory pattern. That's the most important part of the low flow system. The ventilatory pattern must be consistent. It must be regular, okay, for them to qualify. All this stuff we talking about is low flow device. We still in low flow devices, okay? Liter flows of the simple O2 mask is 5 to 8 liters. Less than 5 liters may allow CO2 to build up. Now, the simple O2 mask is less comfortable than the nasal cannula because a lot of people don't like a mask on their face, okay? At 6 liters per minute, it will deliver a higher FiO2 than the nasal cannula at 6 due to the increased reservoir, okay? Because the reservoir is the mask. It's, you know, at 6 liters, it's building up and holding a lot more oxygen than the nasal cannula could, okay? And so that's why you would move to this. If, you know, you got them on nasal cannula, it's up to 5 liters and 6 liters, and they're still not satting well, and let's switch to a simple face mask and see if that works, okay? See if that helps, okay? Now, what was I going to say? Okay, yeah, we'll do that a little later, okay? So that's the aspects of the simple O2 mask. Simple oxygen mask. Now, you're going to have, when this lab comes, we're going to have all this stuff out on the table. And it'll be all switched, you know, mixed all up. And I'm tell you, okay, go get me a simple mask. Set it up. Go get me a nasal cannula. Show me a non-rebreather. Show me a partial rebreather. Show me a Venturi mask. Show me an aerosol trach collar. Aerosol T-piece. Aerosol face mask, right? You have to be able to show me all of these things, all these different devices for the lab, okay? So don't take this for granted. Make sure you're looking at this PowerPoint, do your reading, look at the videos that I already have in there for this lab from other previous labs. It's the same stuff. You need to be prepared when you come to lab, all right? You have your lab book, you know the pages in the lab, you know the dates of the lab. So you better be prepared when you come, all right? Because I'm teaching it to you now, all right? So this is the what? Simple O2 mask or simple face mask. Good, all right? What's the liter flow? 5 to 8 must be at least 5 because
reservoir buildup.
CO2 buildup. CO2 buildup in the reservoir. All right. Partial. This is the partial rebreather mask. Partial rebreather mask. FiO2s can get up to about 60% with a partial, depending on what though? Ventilatory pattern, because we're still in a low flow device. Okay, low flow devices depend on their ventilatory pattern. High flow devices could care how left you breathe. You can breathe 1,000 times a minute if you want to with a high flow device. I'm still going to provide what you need with a high flow device. Okay, so if I see a patient does not have a consistent ventilatory pattern, I'm not even going to waste my time with a low flow device. I'm going straight to my high flow devices. Okay, which is coming up in a minute. The flow for a partial rebreather is 8 to 10 liters per minute. But this is an asterisk here. The flow must be adequate to prevent the bag from collapsing on inspiration. If the bag collapses, then you need to increase the flow. Okay? Key thing about the non-rebreather, there is no valve between the mask and the valve and the bag. There's no valve. Partial rebreather. No valve in it. They got this little thing here, but there's no valve. A little plastic valve, a little rubber valve. There's no valve between the mask and the bag. No valve between the mask and the bag. That makes it a partial rebreather mask. Flow liters of 8 to 10 liters per minute, and you must have enough flow to prevent the bag from collapsing on inspiration. It should never be flat, okay? All right. Why it's called a partial rebreather is because the first 1/3 of your exhale gas goes straight down into the bag from your anatomical dead space, right? We have anatomical dead space, which is all of the conducting airways, right? And so when you first exhale, that gas that's sitting there in the conducting airways goes straight into the bag, all right? The first 1/3 of your exhale is your anatomical dead space, okay? So once you do that first part goes in, all right? So therefore, when you inspire, that first 1/3 gonna come back to you. It's rebreathed, all right? So when I exhale, the first 1/3 of my exhale goes into this bag. And then when I breathe back in, I'm getting that breath right back. You know, you're going to some oxygen too, but you're still going to get the first 1/3. You're breathing your own air back. That's why it's called a rebreather, partially, okay? Partial rebreather, because only partial amount of your gas is coming back. How much of your gas are you rebreathing? 1/3, so partial, the partial, not 3/3, not the whole gas that you exhale, but just a partial part of it, okay? Not to be used at flow rates to increase the patient's CO2. So they saying don't be trying, if somebody, like we always say, if somebody's panicking and they're losing CO2, we put a paper bag over their face. Don't ever get a partial rebreather just for that. That's not what it's for, okay? Don't ever try to use it to trap no CO2. Don't ever do that. You're only using it to give oxygen, all right?
Does the paper bag actually work?
Anything will work if it's trapping that CO2. Because you fall out, pass out because you're blowing off too much CO2. So you put a paper bag over somebody's face, they're blowing off CO2 and breathing it back in. So they're not losing it, okay? Not losing it, it works. Now we have the non-rebreather. The non-rebreather. And in our non-rebreather, we can get FiO2s from 70 to 100%. 70 up to 100% is what we can guesstimate the oxygen to be, depending on the ventilatory pattern. The flow rate on the non-rebreather is also 8 to 10 liters per minute and must be adequate to prevent the bag from collapsing on inspiration. It's just like the partial rebreather. Only thing different between the partial rebreather and the non-rebreather is that the non-rebreather has a valve, a one-way valve between the mask and the bag. There is a valve there. You see that rubber valve? You see that on the camera? Okay. This rubber valve between the mask and the bag. And it also has rubber valves on the exhalation ports to allow air to come out the mask, but air cannot come in the mask from outside, okay? You can blow air out the mask, but you can't suck in air in the mask, okay? Because this valve will block it, kind of like a heart valve. Everything goes one direction. The ventricle can't go back to the atrium. It's one direction, okay? So it's a one-way valve. And this prevents the patient from breathing his own air and outside air. The only gas he gets is from this bag, from the actual source, okay? That's why the FiO2 can be so high, up to 100%. But it still has liter flows of 8 to 10 liters. Make sure that the liter flow is enough to keep the bag from doing what? Collapsing. Look at number 4. 2 one-way valves on the exhalation port, but usually one is removed for safety, okay? So we'll usually take one off for safety. All right. That's it for the low flow systems. Now we are into high flow systems.
What about this other catheter?
Hmm?
We missed the catheter again.
Which catheter?
Transtracheal.
Transtracheal. Okay, I'll go over that in a minute. That's another thing you ain't gonna see. They go straight into the trachea. That's something you ain't gonna see, but we'll go over that in a minute. High flow systems. Let me give it to you. There's transtracheal catheter. If you want to write it in, you can. You're not going to ever see the transtracheal catheter, but there is one, another low flow system called the transtracheal catheter. That's a one little small tube, and that's inserted directly into the trachea. Okay, and they tape it to your neck, and you can use real little oxygen for that one because it's right in the trachea. But you hardly will ever see that one. Okay, you hardly will ever see that one. Yeah, you can just use a half a liter, not even a half a liter, to get a lot of bang for your buck because it's right there in the trachea. It's going straight to the lungs. Because if you put 2 or 3 liters down there, you're going to be 100% oxygen because there's no entrainment of air. Okay. All right, so our high flow systems. High flow systems will do what? Meet all the patient's demands for gas delivered. The total system output must be 3 times the patient's minute ventilation. That is considered to be the patient's demand. So write that down. The patient's demand is 3 times his minute ventilation. That's his demand. 3 times his minute ventilation is the patient's demand. This is due to the 1 to 2 IE ratio. IE is inspiratory to expiratory ratio, usually 1 second to inhale, 2 seconds to exhale. Okay, and so when we all inspiration occurs during the 1/3 of the minute, normal peak flow is about 3 times the minute ventilation. So now all it's trying to tell you is the patient's demand is 3 times his minute ventilation, and you must be able to provide that flow that he needs. Okay, and you can meet that with the high flow system. All right. So for instance, let me do the criteria right quick, and then we're going to do a couple of practice ones. Criteria or indications for high flow systems are the ones who don't meet the criteria for the low flow systems, right? They don't have tidal volumes for 3 to 700. They don't have a respiratory rate of less than 25, and they don't have a consistent ventilatory pattern, right? So if they don't qualify for the low flow, you give them a high flow, all right? Another key point about the high flow system, what's C say? There you go. I can guarantee the FiO2 with a high flow system. Whatever FiO2 I set it to, that's what you get, no matter how you breathe, how fast you breathe, how many times you breathe, or how inconsistent it is. Doesn't matter. If you breathe 1 time a minute or 50 times a minute, I can guarantee the FiO2 with a high flow device. Okay, so we're getting into your toolbox now. What are we going to use for each patient? Okay, now let's look at it. The patient's demand is 3 times his minute ventilation. Patient's demand is 3 times his minute ventilation. So I want you to tell me what Mr. Jones's demand is. What is Mr. Johnson's demand? If erase this, I should be close. What is Mr. Johnson's demand, or Mr. Jones's demand? All right, so let's say, what is demand? Demand is 3 times the minute ventilation. That's the patient's demand. 3 times the patient's minute ventilation is his demand. So what is Mr. Jones's demand? If he has a respiratory rate of 32 and a tidal volume of 650. How many liters per minute is his demand? I want to know what is his demand in liters per minute. Excuse me, let me get a calculator. All right. What is his demand? That's why you go back and make sure you guys are studying all of your formulas and not going anywhere, because now you have to know what minute ventilation is in order to find the demand. If you don't study minute ventilation, well, damn, what is minute ventilation? You got to go back and try to find it. You got to keep them abreast and study every night. What is his demand? Ms. Thomas, you got something for me?
I'm still working on it.
Hey, Ms. Tabor, what about you? Got something?
I don't feel right.
What number did you think?
I got 1350, but that I know it's not right.
What about you, Ms. Rose?
Yeah, I don't think it's right.
Give it a shot. What you thought? What you put?
I got 208.
No. What is his demand? Demand is 3 times the minute ventilation. So you got to find the minute ventilation and then multiply by 3.
I think you start a little bit of like that is probably this.
Close. Minute ventilation.
It's started by minus
No, that's alveolar you're talking about. Regular minute ventilation
so
is,
that 3 times the weight.
that's the tidal volume.
Oh shit, I don't know.
Yeah, that's why you got to go back and look at y'all's formulas. I can't let them formulas go. Minute ventilation, guys, is frequency times tidal volume.
Okay, that's what I did. That's crazy.
Okay? So, if I figure it out, I do 0.650 times a frequency of 32. That equals what? 0.650 times 32 is what?
20.8.
20.8. And then that times 3 is what?
62.4.
62.4 liters per minute is Mr. Jones's demand. He said, I got to have this. If you can't provide this, get out of my room. And so we're going to give him a high flow system that will meet his demands, because we have to meet and exceed his demand. All right? Let's look at it again. What is Mr. Jones's demand if his respiratory rate is 12 and his tidal volume is 500? What is his demand? $18 liters per minute, because 0.5 times 12 is 6 liters per minute times 3, 18 liters per minute. 5 times 12 is 6. All right. So that's how you find his demand. Okay? That's how you find his demand. Now, we're getting ready to go into something a little bit deeper. Let me see what I got in this PowerPoint before I, okay. High flow systems in the PowerPoint meets all the demands of the patient, okay. Total system, your system that you have designed must be at least 3 times their minute ventilation. So that means you got to meet their demand, okay. It's consistent, predictable, and measurable FiO2, right? We're going to guarantee the FiO2 with a high flow system. We can guarantee if I set him up on a 28% Venturi mask, he going to get 28% no matter how he breathes, because a Venturi mask is part of the high flow family, okay? Aerosol trach collar, aerosol T-piece, they're all high flow family. All of them can be set to meet or exceed his demand. Because I told you guys, just because he needs 28% don't mean that's all he needs. He may need more flow, right? So if you get short of breath in your car and the windows is let up, remember we said that? If you're in the car and your windows are up and you start feeling short of breath, the first thing you're going to do is what? Let the window down. But the FiO2 outside is the same FiO2 on the inside. So it's not necessarily an oxygenation problem for you. It's a hunger for flow, okay? They call it flow hungry, all right? And so you need more flow, even though the same flow outside is the same percent of oxygen that is inside your car. So it's not just you need the oxygen, but sometimes they need the flow. So if they're breathing fast and deep, they need you to meet that demand, all right? Not necessarily just the oxygen, because I can put them on 24% aerosol trach collar and be meeting his demand for flow and also meeting his demand for oxygenation, okay? All right, so the criteria for the high flow system we said is the one who doesn't meet the criteria for the low flow system, okay? FiO2, the tidal volume is not 300 to 700. Respiratory rate is greater than 25, right? And they don't have a consistent or ventilatory pattern. If your patient comes to you looking like any one of these gentlemen here, you're gonna put them on a high flow system, all right? Because that ain't regular and consistent, right? That's not regular to be sitting bent over and sweating about to fall out, okay? All right, so before we get into the Venturi Mask, let's talk about the total flow. How much are you giving him? How do I know if I'm meeting his demand? Yeah, I know his demand was 62 liters per minute, but how am I going to give that to him? How do I know if I'm giving that to him? And we do that with the magic box, okay? The magic box. Am I recording? Yeah. So let's show you the magic box so you can get this down packed, and then we'll continue on with looking at these high flow devices, okay? So we do this, and then we're gonna take another break, and I'm gonna get the high flow stuff so you can see those set up, okay? And if they're not in there, we might go over there so you can see the actual mist coming out of it. All right, so this is a concept you must understand. It's called the magic box. This is going to determine how much oxygen am I giving my patient, how much oxygen and how much flow. The total flow of my device. Trying to find the total flow. A couple of steps involved, but once you got it, you got it. You can't take those other things for granted. You have to go back and practice those minute ventilation, tidal volume, dead space. You gotta know how to find that, because when you get a problem that's going to give you some parameters, you got to know how to go back and find what they need to apply it to this problem. Okay, it's not going to give you all of that. It may tell you what is the patient's demand if he weighs 88 kilograms, breathing a respiratory rate of, matter of fact, let's do that. what is the expected demand, right, of Mr. Smith? What do I expect his demand to be? Let me stop the share. What do I expect his demand to be? If I know he is 80 kilograms, has a frequency of, a frequency of 28. Yeah. What do I expect his demand to be? What do I expect his demand to be? Don't forget, demand is 3 times minute ventilation. What do I expect his demand to be? Frequency. Frequency and respiratory rate, same thing. What do I expect his demand to be? I don't know. I ain't looked it up. That's what you got?
I think.
Okay.
Look, I think.
What you get?
44.35.
That's it. 44.35 liters per minute. Good job. So this is what she did. You know that demand is 3 times the minute ventilation. So you got to say, okay, well, what's the minute ventilation? Well, we know that minute ventilation is frequency times tidal volume. Well, we got the frequency of 28, but now we need a tidal volume. The formula for tidal volume is 3 times the pounds, right? So we can say 3 cc's per pound. 3 cc's per pound. Well, what's the weight? 80 kilograms. So we have to take that 80 kilograms times 2.2 gives us how much? 176 pounds. Right? Gives us 176 pounds. So now we got the weight and we have the frequency. Now, what about tidal volume? Tidal volume is 3 cc's per pound. He weighs 176 pounds times 3 is what? 528. So now we can do our problem. Frequency is 28 times 0.528. That gave us 44, I think. No, not 44, but do 0.528 times 0.528 times 28 was what? 0.528.
14 something.
Yeah. Times 28 gives us 14. Yeah, 14.78. You can say 778, whatever. And then take that 14.78 times 3 and gives us 44.35. That's his demand. 3 times his minute ventilation. You had to go around a couple of steps to find minute ventilation because I didn't give you a volume. I gave you a weight. You had to convert that weight into a tidal volume. But you first had to convert the kilograms into pounds and turn those pounds into tidal volume. Okay? That's why you got to know all of these steps. You got to know these formulas that we've already done. You have to know them. Okay? You have to go back and study them. Flashcard yourself. Make up some with your family members, stuff like that. Okay? All right. So that's good. Now we're going to find out if we're delivering this demand that he seeks. Okay? We got to find out if we're going to be able to deliver the demand that he needs. All right? That's called the magic box. Magic box. The magic box will tell me my total flow. Magic box to tell me my total flow of my device. That's what I'm looking for. Total flow. In the magic box, you must put the FiO2. That's what goes in the middle of the box. All right. Now look, on the left side of the box, you put 100 right here always, and 20 right here always. Ready? Ready? Magic box. The FiO2 goes inside the box, and then you put 100 down here and 20 up here. So for instance, I have my patient on a, you're going to learn what this is later, an aerosol trach collar at 35%, running at 12 liters per minute. That's the device I have him on. Aerosol trach collar. Okay, you're going to learn what that is. It's a trach mask with oxygen coming to the trach mask. I have it running at 12 liters per minute, and I have it set at 35% FiO2. Okay, I have it set at 35%, and I have the flow meter cranked up to what? 12. Okay. What is the total flow of this device? And am I meeting or exceeding his demand? Well, let's find out what his demand is. This is what I got him on, and this over here is his demand. This is Mr. Jones. Mr. Jones has a frequency of 14 and a tidal volume of 600. Okay, so you need to find out his demand, and then you'll find out the total flow. And look at it. Am I meeting his demand or not? So first thing I want you to do is tell me what his demand is. 25.2 liters? 25.2 liters is his demand. That's what he demands that you be able to provide to him. All right? So let me do it just to make sure. I trust you, but I got to do it. Good. 25.2. All right. Now, let's do the magic box. What is the FiO2 of the device? 35. So you put 35% right there. Now, we're going to do a little subtracting. 100 minus 35 is what? 65 goes there. And 35 minus 20 is what? 15. 65 divided by 15 is what? 4.3. All right, so 4.321. So this is what you got to find out. When we do the magic box, we're separating the parts. How many parts oxygen? How many parts air? Okay. This gives us the air to oxygen ratio. So this is the air to oxygen ratio. That's what the magic box is giving us. It's going to equal the total flow. We're going to find the total flow out of it, but we first have to get the air to O2 ratio. Remember, O2 is always 1, no matter what. It's whatever to 1. Whatever to 1. Whatever to 1. Okay? You find this part here. This is the air, and this is the O2. 4.3 parts air, 1 part what? Oxygen. So that's the first thing you do. Number one, find the air to oxygen ratio. The second thing you do is find the total parts. Okay, so simple. If 4.3 parts air, 1 part oxygen, the total parts is what? Total is add. 4.3 to 1. So 4.3 plus 1 is what? So total parts is 5.3. All right. Then the last part, number 3, is to multiply. Multiply total parts times the liters per minute that you got them set on. That equals the total flow. So total parts is 5.3. How many liters do we have them on? 12. So 5.3 times 12 is what? 63.6. So the total flow of this one is what? 63.6 liters. Now, he only demands 25. So are we meeting his demand? Yes. We're meeting and exceeding his demand. Okay? Now, I want to show you how the more FiO2 you have, the less flow you want to have. Remember we said that? Because if you cut the windows up, you get a stronger fart, right? If you let the windows down, you have a lower FiO2. So the lower the FiO2, the higher the total flow, because you're pulling in all this outside air. But the higher the FiO2, the less outside air you're pulling in, so the total flow will be lower, okay? And I'm going to show you that with the same problem, but I'm going to show you that. So at an aerosol trach collar at 35% FiO2 running at 12 liters per minute has a total flow of 63.6 liters. That's the total flow. Okay? That's the total flow. Now, what if the patient needs a little bit more oxygen? Now let's see what the total flow is if we increase the FiO2. Watch that total flow go down. You increase the FiO2, you decrease the flow. If you increase the FiO2, you want to decrease the flow. If you decrease the FiO2, you want to increase the flow. Okay? Because of air entrainment. Okay? If the fart is strong in the car, it's high percentage of smell, right? When you let the windows down, you're pulling in all this extra flow now, but the percentage of the smell goes down. So when the percentage of the smell goes down, the total flow in the car is high because you don't let the windows down, okay? So as you increase the FiO2, you will decrease the flow. If you decrease the FiO2, you increase the flow, okay? I'm about to show you. Same patient. Let's find out what the total flow is now. This patient now is on, I got him on a 50% aerosol trach collar at 12 liters per minute. Now what is his total flow? You have to put 50 in here. So everybody look up here. So we put 50 in the box for the magic box because we got him on 50%. 100 minus 50 is what? 50 up here. 50 minus 20 is what? 30. 50 divided by 30 is what? 1.6. So 1.6 parts air to what? 1 part O2. Now, what's the total parts? 2.6 is the total parts. Because it's 1.6 plus 1 is 2.6, the total parts. Okay? Now, what is the total flow? You take the total parts times the 12 liters per minute. 31.2 liters. See how that flow went down? You increase the FiO2 and the flow went down. Total flow went down. Because if you increase the FiO2, you would decrease the flow. If you decrease the FiO2, you increase the flow. All right? Let's look at it again. The last time we had, what was the last one? Was 35%? Okay. Well, what if I have him on 28%? If I decrease the FiO2, 28%. The last total flow was 60 something, right? 61 point something like that. Okay. When it was on 35%. Now we went down on the FiO2. That total flow should go up past that last one. All right, so let's look at it. Aerosol trait color of 28%. What goes in the box? 28. 100 minus 28?
72.
72. And 28 minus 20? 8. 72 divided by 8? 9. 9 parts air to 1 part O2. What's the total parts now? 10. What's the total flow?
120.
120 liters per minute. See that? Went down on the FiO2 and then total flow shot up. Okay? You need to understand that concept. All right, so let's look at another gentleman. What if I have Mr. Jones has a respiratory rate of 32 and a tidal volume of 800. What is his demand? And then let's see what we're going to set him on. We're going to set him on, he is set up on, we got him set up on a aerosol face mask at 60% FiO2 running at 15 liters per minute. I need to know what's his demand, what's the total flow, and am I meeting demand? Meeting? Yes or no? Remember that box you used to give your little person, that note y'all used to give, you like me, yes or no? Check the box, yes or no. Y'all ain't do that. First, find his demand, and then find out what your device is putting out, and match them. Is your device enough for what he needs? Yes or no? Just follow the steps. Should be no problem. What you get? What you get for his demand?
I got 76.8.
76.8. What you get for the demand? For his demand? Okay. Ms. Thomas, what you get for his demand?
I got 17.6.
72.6?
17.
70.6. Okay. You said 76.8? All right. That's what you got? Okay, sounds good. All right, so to find his demand is 3 times a minute ventilation. So the minute ventilation, in this case, is 0.8 times 32, which is 25.6. That's his minute ventilation. Then take that times 3 is his demand, and that should be 76.8. 76.8 liters is his demand. All right, now let's see if we're meeting that demand. We have a patient on a 60% aerosol face mask running at 15 liters per minute. So what did you get for total flow?
I got 30.
You got what?
30.
30. What you get for total flow? Ms. Thomas, what you get for total flow?
I don't have anything down. I'm kind of confused.
Okay.
Yeah, I think everybody reworking it because they got the wrong.
But the demand ain't got nothing to do with this over here.
Yeah.
I just need to know what the total flow is of this device.
I got 30.
You got
What
30?
you say you get?
All right, let's look at it. So if you're not sure, look up here. Watch I do it. What goes in the box? It's probably 30. Let's look. Okay, so 60 goes in the box. 100 minus 60 is what?
40.
40. And 60 minus 20
It's 40.
is 40, right? 40 divided by 40 is what?
1.
1 part air to 1 part oxygen. What's the total parts? 2. What's the total flow? 30. 2 times 15 is 30 liters per minute. Now, am I meeting his demand? No. I am not meeting his demand. He demands 76. I'm only giving him 30. So what do you think I could do to get that flow up?
Decrease the FiO2.
Decrease the FiO2. Let's see. What if I go down to 30% FiO2? Then what will my total flow be? 30 goes in the box. 100 minus 30 is what? 70. 30 minus 20? 10. 70 divided by 10? 7. So 7 parts air and what? 1 part oxygen. Total parts is 7 plus 1. What's the total parts? 8 total parts. So what's the total flow?
120.
8 times 15?
I think I just put it in right. It's 120.
Okay. All right. So then in that case, it jumps up to 120 liters. So now am I meeting his demand? Yes. Yes.
I'm doing all that little now.
But it's the same steps.
I think that is like
It's the same steps though, over and over again. You just need to know the steps. Once you got the steps, you're good. The steps are: first is to find the air to oxygen ratio of your device. Then find the total parts, which you just add them together, and then multiply those total parts by how many liters you got them on. Okay, and that's your total flow. It's the same every time. It's the same every time. Okay, one last one. We're gonna take a break. All right, so let's work these out. You should be able to get this one this time. Okay. All right. Yeah. I got the patient on a. Let's just say 80% aerosol face tint at 20 liters per minute. What is the total flow of that device? And on this side,
the box only works with high.
Yeah, you only use the magic box when you're dealing with high flow system.
Okay.
Because the low flow, we go by the rule of 4s, remember?
Yeah.
All right, so this patient is Mr. Smith. He has a frequency of 10 and a tidal volume of 800. What is his demand? And are we meeting his demand with this system?
Okay, yeah, you do. So, I didn't realize you.
Now work that one out.
Not big one.
All right. So what's the patient's demand?
24.
Okay, 24 liters per minute. Okay, so that would be 0.8 times 10, and then times 3. 24 liters is his demand. Ooh. 24 liters is his demand. Now, what y'all get for the total flow of the device? How much? 25 liters? Okay. So we get 80 right here. 100 minus 80 is what? 20. 80 minus 20? 60. 20 divided by 60 is? How much?
1/4.
1/4.
I don't know.
What's
I
the
got
decimal?
1/4. It's 1/3.
What's the decimal? What's the decimal?
It'll be 33, so it's 1/3. Is it? No, it's 1/4.
20 divided by 60. 23 divided by 60 is 0.3. Okay? So 0.3. 0.3 to what? 1. What's the total parts?
1.3.
1.3. 1.3. Because you're adding this one to this one. So 0.3 plus 1 is 1.3. So 1.3 times 20 is what? 26? 26 liters. So are we meeting his demand? Yes, barely, but we meet it. Okay? That's it. That's it. That's all you have to do. It's the same steps over and over again. All right, so let's continue on. Now we're getting into we're talking about the high flow system. Now we're going to talk about them. Show you the difference between some of them. Of the high flow system. Now these will meet or exceed all of the patient's demands. Okay? As long as you got it set up right. All right, so let's take a break, and we'll come back to showing you some of these high flow devices, starting with the Venturi Mask. The Venturi Mask is the first one we're going to learn about, the Venturi Mask, which is based off the principle of air entrainment. Air entrainment. All right, let's take a break and pause the recording as we break. It's 8 after, come back at 18 after. All right, guys, so now we're on talking about these high flow devices, and let me share my screen. I just taught you the magic box and how to know whether you are delivering enough flow to meet all of your patients' demand. All right, so we're going to talk about some of these high flow devices. The first one we're going to talk about is the Venturi Mask. The Venturi Mask is a high flow device. It's a high flow device, but normally has low concentrations. Okay, FiO2s can around 24 up to 50% on a Venturi Mask. Okay, the reason why it's a high flow system though is because I can guarantee the FiO2. I can guarantee it, no matter their ventilatory demand. So if I want somebody to be on a precise FiO2, then I'm not going to use a low flow device. I'm going to go to a high flow device, and probably the little Venturi Mask is what I would use first. Okay, it's based on the Venturi Principle, and the Venturi Principle simply talks about air entrainment. Okay, air entrainment. So we're going to look at what I gave you. I gave the ones that are here a Venturi Mask, and I want you to look at it as I go over it. This is a Venturi Mask. Okay, it's got one large bore section, and then it will have a small bore tubing on this end. Now, what it is, it has windows. So everybody look right here on the camera. Notice how you see some FiO2s here, right? You see some FiO2s, and then you have some liter flows. You have one group of FiO2s that go with this liter per minute, and then you have another group of FiO2s that will go with this liters per minute, okay? And how you do it is you pull this down. See that? Pull it down, and you turn that arrow to the FiO2 you desire, okay? And so the way they're made, like, what's that, 28%? Let me see, 28, yeah. It's got 31, 28, 26, and 24. So if I want them on 31%, I will open up this and put this right on 31. But notice what's happening. Look at this window down here. As I open it this way, look how big that window gets. See that? You see my window? Look at the screen. You see the window here? And then I can close that window, right? Open that window or close that window. Notice the more I open the window, the less the FiO2. The more I close the window, the higher the FiO2 is going. Open the window, FiO2 is going down. If I close the window, FiO2 is going up. Okay? This is the Venturi Principle. Air entrainment. The more open the window is, the more open that the window is, the more outside air comes in, right? And the more closed the window is, the less outside air can come in. Outside air come in, right? So you have your flow coming from your device, right? And it would be, let me see if I can pull this off of here. So you'd have your flow going from here to your tank, okay? And when it gets to the windows, it will start to entrain outside air depending on how open you have it, okay? So for instance, if I have the windows completely closed and I have 100% oxygen coming from the machine, from the tank, 100% coming all the way through here, 100% right here. If the windows are closed, then it's going to continue to be 100% to the patient, all right? But if I open that window up, so now I'm open, and my arrow is at what? What's my arrow showing? What percent FiO2 is that? No, that's 3 liters. That's 3 liters. Remember, that's a 24%. So they letting you know if you want one of these FiO2s right here, you have to turn the flow on 3. Turn the flow on 3 and then turn this to which one of these you want, okay? And you'll get that FiO2, right? You got to have the percentage and the liter flow, okay? And then if I want one of these FiO2s, then I have to turn it to one of these FiO2s and cut the flow to what? 6 liters on this, happen to be on this Venturi mask, okay? So as I open the windows, that's what I basically want you to understand is the more open the window is, just like the window in your car, the lower the FiO2 or the lower the smell is going to be, okay? If I completely shut he fart and shut the windows, then you stuck with pure smell, okay? And so that's what's happening with the Venturi principle, air entrainment. So as that 100% oxygen goes from your cylinder to here, that's 100% oxygen. But when it gets here, it starts to pull in outside air. And by the time it gets to the patient, it is bled down to the FiO2 that you specified, okay? So if I want him to get, so for instance, I want him to get 40%, and these are kind of hard to see because see how the lines are crazy. So 40% is, let me see, about right there. Yeah, so that's 40%. See that? That line goes to the 40. See that? All right. So if I want 40%, notice it's almost closed, but it's still open. See, they got some little slits, little tad bit slits there, right? And I have to set that on what liters for 40%? 6 liters per minute. And the patient going to get 40% FiO2. I don't care how fast he breathes, none of that, because this is a high flow system. Doesn't matter about his ventilatory pattern, okay? I can guarantee the FiO2 that I give, all right? So this is a pre-made Venturi mask. Comes like this. It's kind of cute. But we also have some that we make ourselves as respiratory therapists. Now, one other aspect of the Venturi mask, look at this little cup here. This cup, it comes off, but this cup fits on there like that. It serves 2 purposes. For one thing, if the patient is doing this and breathing, I can give him a breathing treatment through here, okay? I can give him a breathing treatment through here with the little nebulizer right here and give him his breathing treatment at the same time. The main reason is to protect these windows, okay? Now, what if I have a COPD patient on a Venturi mask at 28%, okay? He's getting 28%, he's a COPDer, right? So I want to be careful on the amount of oxygen I give this patient, right? I want to make sure he's not getting too much, right? Well, what if Mr. Johnson is in the bed with his Venturi mask and you come in the room and the Venturi mask is under the bed sheets and he's watching the game? How much oxygen is he getting? Yeah, he's getting oxygen.
He getting a lot because it's covered up.
It's covered up. So I'm covering up the windows.
Yeah.
The windows are closed now. So he's getting pure deoxygen. See what I'm saying? So this thing here is supposed to help protect from bed sheets and covers. So if a sheet laying on there, it's still getting some air entrainment in there, okay? So it protects those windows. It protects the air entrainment. So make sure that the air is getting in like it's supposed to, okay? If it's not getting in and his little bed sheets are completely covered, he got his cold. And he got the cover on, another cover on, and this under the cover. The tubing is out to the thing. He's getting oxygen, but he's getting 100%. Then you go back in the room and he ain't breathing, okay? So you have to be careful. And that's why they use these little protections right here, the little protection cup to protect the window. And I can also stick a large bore tubing on it to give him a breathing treatment. So I don't have to take this off and put another mask on for breathing treatment, okay? Now, one of the disadvantages of this, say he's on 20, let's say I got him on 28% Venturi mask, right? 28%. How much is that? 28%. He's on the Venturi mask. Now, if I take the oxygen away, his oxygen drops. He got to have the oxygen, okay? But he can't eat because every time he takes the mask off to eat, his oxygen drops. So you as a respiratory therapist, what would you recommend and how much to prevent that from happening so he can eat? What would you do? So think about all of your stuff that we've shown today. He's on nasal cannula, how much? 2 liters. Switch him to a nasal cannula at 2 liters because that's going to give him about how much? What percent?
28.
28%. So I put him on a nasal cannula at 28% and let him eat. Now he can eat, he can talk without losing his oxygen. Okay, your sticker's on your neck. Oh, there it is. So if they own 28% Venturi mask and you want him to get 28%, but every time he take his thing off and try to take a couple of bites, he short of breath, he start getting blue, he have to put this right back on, right? Well, Mr. Johnson, what we're gonna do is just put you on a nasal cannula at 2 liters, which will give you about 28%, as long as he's breathing regular and calm, right? I can give him about 28% and he can eat, all right? So that's the kind of decision you would make on your own as a respiratory therapist, all right? Well, let's switch him to a nasal cannula at 2 liters, all right? And if he's on 5 liters, if he's on 40% Venturi mask and he take it off to eat and drops, then you recommend a nasal cannula at how many liters? 5 liters, okay? All right. So that's a Venturi mask that's pre-made. I'm gonna show you one that we make ourselves. You're gonna also be seeing these sometimes. These colorful. These are Venturis. Each color is its own FiO2. So what's the FiO2 of the blue one? Hard to see, but just see that? There it is right there. I can see it.
24.
24%, and as long as I turn the flow is on what? 2 liters. So as long as I put it on 2 liters, you're going to get 24%. And this is how it's made. You take the Venturi piece, right? Because all of them have a different orifice inside of there. See how small that hole is right there? That little bitty hole. You see the little bitty hole? See how small that is? And then if you take the pink one, which is 40% oxygen, they're always the same. Pink is 40%, okay? So pink, see if you can see the 40 on there. See that 40? 40% as long as I turn it on how many liters? 8 liters. See that hole? Look how much bigger that hole is. How much bigger that hole is compared to that hole. See that? So it's more oxygen is getting through, right? And so that's how they make their Venturi device, right? And this is easier because it's easier to deal with. So I would take one of these, say I want a patient on 40% Venturi mask, and I got to make it myself. I don't have these little expensive ones, right? Well, I take the 40% pink one. I put my 1 section of large bore tubing on here, right? And then I put my, I brought my stuff in. Give me that bag, that mask that's in that bag right there. All right, an aerosol mask, a regular little aerosol mask. It's the same kind of mask you see on breathing treatments. It is. This is what's called an aerosol mask. It's got big holes on the side. You can either put your breathing treatment right there or one of these systems. Okay, the aerosol mask is multi-use. Okay, so I got the Venturi, the tubing, and the mask. This is the same thing as this. Same thing. The Venturi, the large bore tubing, and the mask. Same thing. But I made this one. So now if you don't need 40 no more, I can just use another one, right? And make it myself. Much more cheaper than the one that's pre-made, okay? Now, of course, I don't have the little protection, because this protection cup doesn't fit on these, because I don't have that one no more. But you do have a protection cup that comes with these, okay? It'd be just like this, but it's made where it will fit down in there, and it will be just like this, okay? This is your 40% Venturi mask, all right? If I use the blue one, it's 24% Venturi mask. If I use the orange one, let me see, get it to focus. Can you see that one? Let me see if I can see. This is a 50% at 12 liters. Okay, so long as it's a fit, this is a 50, so it's bigger than the 40. See how big that is? And let's look at the 40%. Well, this is the 50, and that's the 40. So that's a little bit bigger, not much bigger, but the 50 is a little bit bigger, okay? So that's the Venturi setup that you set up. So when you come to the lab, I'm gonna tell you, set me up a homemade Venturi mask. You will look for aerosol mask, one section of large bore tubing, and one of these, okay? And if I say 40%, you get the pink one. If I say 50%, you get the orange one, right? You can look at it and pick up then. You got a white one. The white one is 31%. The yellow one is 28%. Is when you'll see the most, because everybody's usually on 28% or 2 liters in the hospital, okay? And then again, the blue one is 24%. So that's our homemade Venturis, right? We keep them in the homemade Venturi bag. That's our Venturi system, okay? That's the Venturi system, guys. Now, that Venturi mask uses the same Venturi principle on other devices, okay? So the Venturi system is the system of air, and what's that called? Air, the big word, air. The Venturi system is a system of air, what's it called? The E word. Entrainment. Air entrainment. That's the Venturi system. Air entrainment. Okay, it's entraining outside air. Another good, it's the word for sucking in air. Okay, it's sucking in outside air to bleed the FiO2 down. The more flow, the lower the FiO2. The higher the flow, the less the FiO2. Right? We just showed that with the magic box with mathematical. Shows you it's going to go down. If you increase the flow, the FiO2 is going to go down. If you decrease the flow, the FiO2 will creep up, just like the windows in your car and the smell, okay? All right, now, bigger than that, sometimes we need to give a patient a little bit of moisture with that high flow, okay? The Venturi mask is a low, it has low concentrations, but it's a high flow system, okay? But when we go into the aerosol systems, okay? Aerosol this, aerosol that. Anytime we put water on it, it's called aerosol, okay? So let's look at the aerosol setups. This is the aerosol. One large bore tubing, 2 large bore tubing, drain bag, whatever's on the end. All right. The aerosol setups are also high flow devices that use the same Venturi system, except it encompasses water. So not only is it the Venturi system, see the windows up here? See how I close that window? Or I open that window? Close the window, see it's closed. Or I can open it up, right? Air entrainment or no air entrainment. Okay, notice how it corresponds with the numbers. So it's totally closed, right? The windows are closed at the top, right? Okay, now what's the FiO2 say? 95. That's a 9. It's probably hard to see. 95%. See that? So 95%. See the little arrow? This arrow right here is pointing at 95%. Windows are closed. As I open the windows, look at the FiO2 go down. What's that? 80. What's that? What's that? 50, 40, or 35, right? 35%, look at the windows, wide open. Because coming in here is 100% oxygen coming from the flow meter. But once it gets there, it sucks all that outside air in and it bleeds it down to 35%. If I close some, I can get 40%. Now look at the windows. They still open, but a little more closed, right? Then I go up to 50%. The window's still open a little bit. See how smaller it's getting, smaller and smaller.
Does it tell you what flow it has to be on?
Yes, it does, right here. On this bottle, it tells you your total flow.
On the label.
See, the label tells you your total flow. So for instance, it says if you have them set at 35% and you turn the flow meter to 14, you should get a total flow of 74 liters per minute. Okay, that's what it, look at the top line. I don't know if you can see it or not, but the top line says if you want them on 35%, you put the O2 liters on 14 and you get a total flow of 74 liters per minute. Okay, so if you work that out yourself in the magic box and you put 35% at 14 liters per minute, you're gonna get a total flow of 74. Okay, and so they tell you that, or if they don't have that, you know how to figure it out. Okay, you know how to figure it out. So there's another principle that's involved with this Venturi principle when you're dealing with water, and that's the Bernoulli Principle. Bernoulli Principle, which talks about the water going through a tube. Okay, the water will go up through the tube and create a mist. So not only are they getting that good flow and oxygen, but they're also going to get some mist coming out of there. Basically because a lot of times we use this for our artificial airway patients. Remember we said if you bypass the nose, that gas has to be heated and moisturized because the nose does that job, right? The upper airway will moisten and heat the air. And if you bypass that nose, like on this gentleman here, he no longer uses his nose, he uses his trach. So everything going in here is pure dry, and you're gonna dry his lungs out unless we put some moisture on it, okay? We're gonna put some moisture on it to keep him from drying out, all right? So we're giving him the oxygen, the flow, and the moisture because his nose has been bypassed.
So what about the heat?
Some hospitals will do heat, some of them don't. Some of them say that the heat breeds more bacteria in the hospital, so some of them won't do a heat. Some places will do a heat and have a heated little thing that covers the bottle and it'll heat the water. And so it gives, some hospitals do, some hospitals don't. MBRC hospital wants you to heat and humidify, okay? MBRC hospital wants you to heat and humidify this gas.
If they don't, you can do something?
Not necessarily. I'm telling you, it's a tomato type thing. Some hospitals say yes, heat it up. If some hospitals say no, we're not going to heat it up because the heat breeds more bacteria. Okay, and so I may give them an infection quicker with some heated aerosol than I would some cold aerosol. Okay, so but NBRC hospital, which you're working at the NBRC hospital in school, and they want you to heat and humidify. So all your answers need to make sure you're heating and humidifying that gas, okay, to an artificial airway. What about somebody who just got extubated? The tube was down your throat to get those butt shots or whatever kind of cosmetic surgery. You weren't really sick. What I'm trying to get you to understand is you went surgery not to be sick, but a little quick surgery that they had to put you to sleep for, okay? We're going to intubate you. We're going to tell you to breathe this little gas and you're going to go to sleep. You ain't going to know what happened. But when you fell asleep, we intubated you. We opened up your mouth with the scope and went straight through your vocal cords with the tube. That's intubating a patient and putting them on life support. You're on life support when you're in surgery, okay? And then when you're done with surgery, they cut down the anesthesia and they extubate you, pull the tube out and put the little mask on you like this with this and this little aerosol, right? It's a little cool aerosol to keep the throat cool. And then that's when you wake up with this mask on. You never knew you was intubated, but your throat might be a little sore. That's because you was intubated, okay? You'll learn intubation in 220. But we as respiratory therapists are the ones that intubate. Respiratory therapists are the ones that intubate, okay? You're gonna have to know how to intubate a patient.
Yeah, I knew. I thought it was a lot more training than next term.
It is. I mean, it starts next term, starts in 220. You're not gonna be intubating in the hospital at all, not till you graduate. You're just going to be learning how to intubate on the mannequin and knowing what to look for and all of that. But you will never be intubating as a student in the hospital. They ain't going to let you do that. All right.
They can wait till we get the job and then say, oh, okay, go intubate.
Well, you're trained to do it. Just like ABG, just like anything else, you're trained to do it. And then some hospitals will make you go to surgery and do about 3 or 4 of them every year to get checked off on to make sure you're doing them properly. So you'll go sit with a surgeon, anesthesiologist, and every time they do, it's controlled, right? Because they're putting the patient to sleep. Everything is nice and controlled. But on the floor, when they crash, people are doing CPR, and you're trying to intubate, all of that's happening. You got to be a real deal respiratory therapist does that. You can't be like, oh, I ain't doing that. That's not a therapist. You're either gonna be a breathing treatment giving therapist or you're gonna be a therapist. okay? If you're a therapist, you do it all, right? In the ICU, somebody's dying. You ain't got time to be worried about this. That's why you need to be on your game so that you can save them from dying, because you intubate, you put them on life support, you monitor the life support. That's why respiratory therapists is needed so bad with the coronavirus. They hiring $5,000, $10,000 a week for respiratory therapists because they need them to run these ventilators, intubating these patients. That's us, okay? That's why we don't put just anything out there. We're gonna put the best qualified trained therapists out there in the field representing what we do, okay? This is real, this ain't MA, this is respiratory, okay? There's a lot of things you're gonna be doing. This is just the foundation of what to look for. And then you get to 220 and 230 and 240, 250, you learn all those higher concepts. All right, so let's look at the aerosol setup. This is the aerosol setup. Now, write this down. Whatever it's called is what you put on the end of it. Whatever you put on the end of it is what it's called. Aerosol, whatever, okay? Whatever you put on the end of the setup is what it's called. That's the name of it. It's an aerosol, whatever you put. Okay, and I'm gonna show you the different things you put on the end. Aerosol this, aerosol that. What I was showing y'all earlier when I was saying aerosol T-piece, aerosol trach collar, aerosol face tint, all right? Those are the different pieces that go on the end, all right? So here it is. You first start with this bottle is called a large volume nebulizer, okay? This is a large volume because it has a lot of water in it, a lot of volume of water, okay? Large volume nebulizer that utilizes the Venturi and Bernoulli principle. You will have this bottle, we have a top on it and have a plastic bag when they're full stored in respiratory. And then these are stored alone as well, okay? Because you might just need one of these or might need another bottle because it's ran out and now it's time to change the bottle. And so this is the Venturi piece here, right? This goes onto the flow meter. This is your Venturi window, right? Determines your FiO2. See that? Those are the FiO2s there. 35% all the way up to about 95%. With the windows up here, okay? This here is the Bernoulli principle. This goes down into the water and sucks up the water and gas through a tube. That's based off the Bernoulli principle, okay? So it's two principles involved with this aerosol setups, the Venturi and the Bernoulli, okay? Two different scientists, Venturi and Mr. Bernoulli, okay? Now, so this goes in here like this, and then you just screw it on, okay? Now, you need one large bore tubing, the first large bore tubing, hey. Oh, okay. So one large bore tubing goes on here, right? Onto the actual large volume nebulizer, okay? And that's going to be bringing all kind of moisture through here, okay? That's going to be aerosol particles floating through here. So eventually, those aerosol particles are going to fall and turn into what? No. Those aerosol water particles will eventually condense and come together and turn into what? Water. Water, like rain, right? When the rain, aerosol particles in the air, the fog you see, that's aerosol. It raises up to the clouds, and as so much gets there, it starts to coalesce. They come together. One drop, come with another drop, and they get so heavy, they can't stay suspended, right? And once they can't stay suspended in air, they fall to the ground as rain. So that's called rain out. Okay, so you have to anticipate that aerosol, that beautiful aerosol coming through here, eventually is going to rain out because it's either going to get cold, the patient's room might be cold, right? And it's coming together and they coalesce. So you don't want that water to go down in his trach, so you have to have what's called a water trap or water bag after the first large bore tubing. Okay, so you have the large volume nebulizer, you put one large bore tubing on here, and then your water bag. Okay. And then your second what? Large bore tubing, right? And this goes to the patient. Simple as that, okay? You have sections on these large bore tubings that you can cut, okay? So you usually try to put the bag wherever the trough is, okay? If I have a patient on it, just say this was all I had, and this was what I had. Where is the trough at in here? Where the water gonna collect at? Right here, right? So if I know that I got grandmama right here in the bed at home, and I have the system over here, and I see that this is where it's going to, the water, if it starts to collect, it's gonna collect right here. So I'm gonna cut right here and put the bag in between there. That way the bag is there to catch the water that collects. Okay, just simply by gravity. And this will be 1 and this will be 2, and have my bag in the middle. Okay. But for our sakes, we have 2 large bore tubings that we connect them with a water bag. This water bag will catch the excess water as it rains out. Okay. And then you have this end, which goes to the patient. Now, whatever I put right here is what it's called. This is aerosol. Say aerosol. Face mask. Say face mask. So if I put this on here, this system is called a what? Thank you. If this is called a face tint, this is a face tint for people who have burns. If your face has been burned, they had a bad house fire and they're in the ICU and they're burned, you don't want to put this on their face. You don't put a mask on, right? This is a face tint. It just hangs right here and the oxygen comes up like that so they can breathe it. If they just had oral surgery or gunshot stabs in the face, you can't put nothing on there, right? You have to keep it off the face. So it's called a face tint. So if I put this on here, this is now a aerosol face tint, okay? If the patient has a tracheostomy, like this gentleman here, if he has a tracheostomy, then you use what's called a trach mask. This trach mask goes over the trach just like that and then snaps around the back of his neck, okay? It fits right on like this and it snaps on the other side. It's like a little snap thing right here, and that's how it sits. That's a trach mask, okay? This is sits right over the trach so oxygen can go in and out the trach and with the moisture. So if I put this trach mask on here, or this is also known as a trach collar. I call them trach collars. Some people call them trach mask. Same thing. But for my class, I'm going to say trach collar because that's what I'm used to, okay? This is a trach collar, all right? It's just like a collar for your trach. If I put this trach collar on here, this is a, that ain't hard, is it? This is it, okay? And so if I have them on 40% aerosol face mask, okay? I'm gonna find the face mask, set up my aerosol setup. He's on an aerosol face mask, and I'm gonna turn the Venturi to what? 40%. Screw it on to the flow meter and cut it up to the flow I'm supposed to have. And he's getting 40% no matter what.
So how do you connect the?
It's gonna go just like this.
Oh, sure.
Screw right onto our flow meter.
I was definitely not expecting. I thought he was gonna hook another tube.
This is your flow meter. This is your flow meter, just like this. If this is coming out the wall, you plug it up, screw it to that, and turn your flow to whatever, okay? This is your flow meter. So I'm gonna cut my system on, right? My H cylinder is on. I have the patient on an aerosol. Let's see, what we want them on. Aerosol face mask. Aerosol face mask at 40%. And I'm going to cut him on. I'm just going to cut it to where you can see it. See that? You might not can see it at home, but it's, you see that coming out of there? You don't see that mist shooting out of there? You gotta kind of look at the dark, something dark behind it. See it? That's aerosol coming out of there. You see it? So if you can't see it at home, this is aerosol coming. It's like a little fine smoke coming out of there, okay? And so that is my system. I have them on. What I have them on is a aerosol face We're going to say aerosol face mask. Okay, so that's going to be coming eventually through here. It's hard to see. See that? See that on at home now behind this green cylinder right here? Let me see. You see it on the camera? Okay.
You can see it faintly.
Okay, good. So this is an aerosol coming out of here, okay? And that's 40%. Well, let me see what I got it on. Yeah, 40% at 15 liters per minute. And this is it right here. This is 15 liters per minute of 40% oxygen coming out of here. And it's nice and cool and moist, okay? Pure oxygen. This is pure oxygen, but it's been bled in, see? And outside air is entraining into these windows right here, right? So now this should be 100%, but since I have the windows open, outside air is coming in and bleeding the percentage down to get to what I said, which is 40%, okay? If I want them on 100%, I close the windows. See how the sound went down? See that? See that? See how the sound went down though? You increase the FiO2, you decrease the what? When you increase the FiO2, you decrease the flow. And you can hear the flow has went down. It ain't real loud no more. It's 100%. I got it set on 95%. So this is 95% oxygen coming out of here with some aerosol, okay? And since you don't hardly hear it, it's because I turned the flow down. But if I decrease the FiO2, it's on 95% now. If I decrease it to 35, listen to the flow. See now how loud that is? Because it's sucking in all that outside air. And you barely can see it now because there's so much more flow coming through there. It's coming out, but you can barely see it, right? Now, so of course I got one large bore tubing, then I have to have my water bag because eventually that water particles are going to coalesce, that means come together and rain out. And I want it to rain out into my bag. So then I have this little plunger here. I can open it up and drain the bag out whenever it fills up, okay? The other end goes to my patient, okay? So what is this? Aerosol trach. I'll say the whole thing. 40% aerosol trach collar, because that's what I got it on, 40%, okay? Running at 15 liters per minute. Okay, so I'm gonna let y'all see on camera. 15 liters per minute, and it's a 40% aerosol trach collar. All right, so say it again. 40%. All right, what is this?
40% aerosol trach tint.
Aerosol face tint. This is a face tint. Yep. So I have it on just like this. So I don't have to touch my face, but I'm getting all that good old oxygen through here. Okay? Makes you feel good too when you get oxygen. And then what is this?
40% aerosol face mask.
All right. There's one more to go, and that's the aerosol T-piece. Say T-piece. T-piece. Like Tom. T is in Tom. Aerosol T-piece. And that is when I want to, it makes a T. And that's what it looks like this. I have to use what's called a Briggs Adapter. Everybody say Briggs Adapter. Briggs Adapter or T-piece. That's how it makes a T. This is a T. This is really called a Briggs Adapter. So if they ask you or say, use that word, you need to know what they're talking about. This is a T-piece, also known as a Briggs Adapter, okay? So it's simple, same thing, except for this time, this end coming to me, look right here, this is the end coming to me, I put T on one end and another one on, oh, that's why I did that. Another one on this end, and this, because I want to fit this one. Some of them don't fit. You got to find the right one, but I ain't gonna worry about it. This is what it looks like. See that? T-piece. Right? Now, what's important about the T-piece is, guys, make sure you write this down. When I have an aerosol T-piece, that goes right over my trach. See, it can go over his trach like this. See that? It can fit right over his trach like that, so he's getting his oxygen. Or if they had an ET tube down his throat, right? The ET tube, that when you intubate a patient and have a tube coming out their throat, I can sit this right over the tube. We use this, guys, to wean the patient. I'm trying to see if he can live without the machine. So if he is on a, if he has a intratracheal tube, which is an ET tube, out his throat, and he's on the machine, the life support. When I'm weaning my patient, before I pull that tube and say, let me see, can you do it? Right? I ain't gonna do him like that. I'm going to wean him down off the support first. And then once he is wide awake and he's breathing spontaneously, then I can say, well, let me take the machine off and just hook this up. Because this is not pushing any volume. This is just blow by oxygen. If he's okay with that, his sats stay up, his heart rate is still good, he's like, I'm good, take this tube out, right? Then we can pull the tube. But if I pull the tube and he ain't ready, I got to intubate him again. And that takes paralyzation. And then you got to give them some medicine because they mouth be biting down. When people are fear and dying, they bite down, they lock up. You have to give them what's called succinylcholine, right? Acetylcholine, we call it sucks, or rocuronium. And those are paralyzing agents. They hit him with that in the IV, totally let go, right? Mouth, everything. But he ain't breathing either. It paralyzes his respiratory drive as well. So you have to hurry up and get him intubated in that case, okay? And so instead of going through all that again, right, I want to test him to see if he can deal without being on the machine, right? And if he can, we try it with the T-piece, right? Take the machine off of him and just hook this right to the end of the tube, right? And see if he can handle that. If he can handle that without a problem, he's ready to be what we call extubated, okay? It's either intubated or extubated, all right? And so, because I said, I don't want to go through the risk of pulling the tube and he ain't ready. Because if he's not ready, his sats going to drop, he's going to be huffing and puffing, his heart rate going to go up, he can't breathe. He's not ready. He's not healed enough to be off the machine, okay? And so we can test them with an ET tube with a T-piece, all right? Or the patient might have a trach, and we can just stick this right over the trach, just like this. And that's a T-piece. This is aerosol T-piece. So what is he on?
Aerosol.
What's the percent?
40% aerosol T-piece.
There you go. Okay. Now, one other thing about the T-piece. Smoke's going to be coming out the end of here. Okay. The mist. All right. The mist should be coming out the end here. If the patient inhaled, and just think back to the non-rebreather mask, and we said that bag should always stay inflated, right? So what if that bag deflates when he take a breath? What are you supposed to do? Bump up the flow. So if the mist that's coming out of here, when he breathes in and that mist disappears, you need to increase the flow. You should always see mist. If I breathe in and suck all the mist back this way, that ain't enough flow coming through there, okay? You should always see mist coming out of here. Even when I inhale, there should be still a little bit of mist coming out. If I don't see the mist every time I inhale, that's just an indication to crank up the flow, okay? Turn this flow up a little bit, all right? You should always see mist coming out the end of a T-piece, all right? You good, Ms. Rose? Every time you're on a T-piece, always watch for that flow. You should still see the mist coming out. If you don't see the mist coming out, that means you need to increase the flow. If you think back to the non-rebreather mask, if he takes a breath in and that bag deflates or collapses, you need to increase the what? The flow, okay? So that's the only little trick about the T-piece that you need to remember is that one thing is called the Briggs Adapter, right? This little T-piece, we always say T-piece, but this is known as a Briggs Adapter. And the Briggs Adapter must be on the end. He must watch for the flow.
I'm sorry.
Okay.
Okay, yeah.
All right. So that's an aerosol T-piece. He's on 40% aerosol T-piece. Now you notice, if you can see, it's starting to bubble up right here, right? That mist is starting to collect. See that little mist in there, that water droplets? It's starting to collect. Over time, it's going to start coalescing. It's going to drop and turn into water. If I have my patient on a T-piece and I don't have a bag in the middle, that water going right into his what? His lungs. So you got to have that bag. So your parts to the high flow system, as far as the aerosol is concerned, see that? The parts will be the large volume nebulizer, right, which has the Venturi Principle and the Bernoulli Principle for that tubing inside of there, okay? The large volume nebulizer, one large bore tubing, then you have to have a reservoir bag or water trap, water bag, whatever you want to call it, and then another large bore tubing, and then whatever you put on the end is what it is, okay? All right, so Ms. Rose, what do I have first? Large volume nebulizer, also known as an LVN. LVN, then you have what goes here. Large, say large bore, because large bore and small bore mean a lot, okay? So these are, the corrugated tubing is large bore tubing. So one large bore tubing goes here. All right, then what? What goes after that first large bore tubing? Your water bag, right? And then what goes after the water bag? Another large bore tubing, and then what goes here? Whatever you want to put it, whatever you put. Aerosol face mask, aerosol trach collar, aerosol face tint, or aerosol T-piece.
So what's the water called again?
Aerosol.
No,
This is the large volume nebulizer. Because it nebulizes water. Aerosol, you can see. Humidity, you cannot see. We'll learn that when you get to aerosol humidity, which I think is coming up after this section, is aerosol and humidity. And we're going to talk about the importance of the humidity and what happens if you don't humidify air. But for this test and this unit, we don't get deep into the humidity right now. I'm just showing you that this is an aerosol setup, which is a high flow system. Okay. Now, this bottle may look like anything. As long as if it's a bottle with water in it and it's got the Venturi system on there, that is a large high flow system. Same thing. They just come in different packages. All right. This is the one I happen to like. We also have some over there that's a smaller bottle, about this big, but it will hook to here and it has a Venturi. If it don't have the term Venturi, it's not a high flow system. Okay. If it doesn't have this Venturi, it's not a high flow system. All right. Only the high flow system will give me a guaranteed FiO2. Okay. So you'll have a bottle of water and a little adjuster on there for the FiO2. It'll have a little mark and it have the FiO2s written on there. Okay. Now, quick question. Sometimes the nurses make this mistake. When they are, what if the patient doesn't need oxygen, but they have a trach collar? If they have a trach, but they don't need oxygen, then what am I gonna have this hooked up to? No, he got it on here. He got it on him, but he doesn't need oxygen anymore. He don't need. His oxygen is great, but he still has an artificial airway. So I still got to do an aerosol setup, okay? Because I got to give aerosol, okay? But what would I have this screwed on to?
The mask.
No, this part, this right here. What do I screw that on to? If you don't need oxygen, then what am I gonna be using?
The trach.
What gas am I using, guys? If he don't need oxygen, the yellow one, the medical air. I have this hooked up to medical air, okay? Because he don't need oxygen no more. He just needs that moisture because he has an artificial airway, okay? Now, what the trick is, nurses make the mistake of saying, oh, he on 35%, he on 40%, but he's on the air tank. I don't care what this say, he only getting what? Medical air. So a lot of times they make that mistake, all right? Or they'll chart in the notes, he on 40% trach collar, but he's not. He's on 21% because he's on the yellow tank, all right? Because when they get to the post, you always want to wean them off the oxygen, right? So say he started out at 40%, you got him down to 28%, he's doing well. Oh, we're gonna unscrew this and hook it to the air now because he don't need oxygen no more. He's healed enough to not need oxygen, okay? But he still has an artificial airway. I can't just blow no nasal cannula on here. I have to give him the moisture. He's going to be, for him, will be the trach collar. So he's going to be on aerosol trach collar at 21%. okay, because it's on room air, all right? So no matter what this says, no matter how much air you entrain or don't entrain, this is room air if it's yellow, okay? Outside is room air. So no matter if it's coming in fast or slow, it's still 21%, okay? All right. Make sure y'all go back and look at this video. But, you know, it's just a lot of information, but once you got it, you got it. This doesn't change, all right? There's no new setup that you're going to have that you haven't learned today, okay, as far as the high flow devices, except for the machines. You will get to them, which is the ventilator. That's a high flow system because I can set the F out too. The BiPAP machine, right? Those are all high flow systems. CPAP machine, those are high flow systems, okay? All right. Let's go back to the PowerPoint, see what we missed. All right, so we already showed you, I talked about all this. Let's go back and look at as far as the notes are concerned. Venturi Mask, we said it is a high flow system, about 24 up to 50%, depending on how you turn the wheel, right, or open the windows. It has the Venturi system and the Bernoulli system. Bernoulli is when a gas passes through a restriction, radial pressure decreases and velocity increases. So as gas goes through that tube, the radial pressure decreases and the velocity that's what's causing the suction from the Venturi, okay? When I turn this on, what makes the air go in is that Bernoulli principle, right? Because it's sucking up gas through that skinny tube, and that makes the radial pressure decrease, but the velocity increases, and that sucks in air from outside, okay? You don't have to remember all of what I just said. Just know it's Venturi and Bernoulli, okay? The Venturi is the one with the windows. Bernoulli is the one with the little stem, okay? All right. Venturi setups use a specific entrainment ratio. Remember we said air to oxygen ratio. That's also known as the entrainment ratio, okay? The same FiO2 always has the same what? Ratio. So in your book, I hope you guys are reading, there is a table in your book that shows you all of those ratios that you did with the magic box. The only reason you use the magic box is if you don't memorize what they are, okay? So what is 40% air entrainment? Tell me what that is. What is the air to oxygen ratio for 40%?
We're doing the Vectory ceremony.
Okay.
Next a few minutes.
All right. What is the 40% air entrainment ratio? Tell me what 40% is. Just do the magic box for 40% and tell me what the air to oxygen ratio is. And then we'll go out there and check that out. I don't want the total flow. I just want on the ratio.
Oh.
3 to 1. So 40% is always going to be 3 to 1. Always. That's what they said. Same FiO2 always has the same ratio. Okay? So 40% FiO2 will always be a 3 to 1 ratio. You didn't get that? Put the 40 in the box. 100 minus 40 is 60 on top. 40 minus 20 is 20 at the bottom. Okay, so 40% is always 3 to 1. I'm going to pause the recording here, guys. They're having a veteran ceremony right quick. I'm going to pause the recording and we're going to come back. Okay, guys, we just had a veterans ceremony really quick, and we appreciate all of you students that have served in the country, whether you were at war or not. I know we have 1 or 2 in our class this term, and we thank you for your service, and anybody whose family members who served, we thank you for your service. All right, so Venturi setups, as we just said, the same FiO2 always has the same ratio. So you guys just figured it out for me. 40% is always 3 to 1. If you do the magic box for just the air to oxygen ratio, we see that 40% is always 3 to 1. Okay, and all of the rest of them have their ratio. If you memorize it, you can memorize it, or if you forget, then know how to do the magic box. Okay, the magic box sheet is in the module. You can go back and look at it. It's got step-by-step of what to do in the magic box. It's also in your reading. Please don't go away from the reading, all right? Some of the stuff on the test may be from the reading that you didn't get during lecture. So if you can't blame it on, I didn't get that, and we didn't talk about that. We might not have, but you read about it, all right? Now, altering the flow will not alter, flow rate will not offer that ratio. No matter what the ratio or the FiO2 is, that ratio is always the same. 40% is always 3-to-1, whether we got it on 10 liters, 5 liters, 100 liters, whatever it's on. The ratio remains the same. Now, the total flow will change, but the ratio does not. Okay? Now, anything other than the prescribed flow rate will give the same FiO2 unless there's less flow. Now, number 2, altering the flow rate will alter the total output, right, or the total flow. And we just showed that because we take the air to oxygen ratio, which is the parts, and then we add the parts and get the total parts, and then we multiply the total parts by the what, Ms. Rose, to get the total flow? Liters per minute. And that's going to give us our total flow. So naturally, if the liters per minute is different or higher or lower, it's going to alter our total flow. But the ratio does not change. Okay, now this is said FiO2. We're talking about the Venturi Mask. It says watch for the what? What's number A? Say watch the what? Right here, the bed sheets. Because if the bed sheets block that port, the air entrainment port, you're going to increase their FiO2. Okay, now I showed you the pre-made Venturi Mask. I showed you the homemade one that we make, and that's these right here. Right, so now you can see them up close. The orange one is 50%. The pink one is always 40. The green one is always 35, and so on. This one here, this is another one that's sophisticated. Look at this one. This looks even more sophisticated. But you have an arrow pointing at what? How much percent is that? 31. And what's the liters that you got to put it on? 6. So that's what they're showing you. Down here is 50 and 15, 45 and 12, and so on. Okay. So this is just another example of a Venturi setup. These are also Venturi setups. Okay. If you block that entrainment port, then you now are getting 100% oxygen. Okay. We showed you that the insides is where you see the difference. All these windows here are the same. Okay. They're made the same. It's the inner port that's different, right? And that's the inner port inside here. When I showed you this inner side, right? This is the 50%. See how big that is? And then if we compare that one with the 31%, see how small that is? That's the difference. But these windows here are the same. This one and this one, they're exactly the same. The difference in the entrainment are the inner inside. See how this one's small and this one's huge, right, for 50%. Okay? So these are examples of Venturi setups. Here it is again. This is the Venturi setup for your notes. You have the mask, you have your large bore tubing, and you have your air entrainment port, also known as the jet orifices inside here, and this is your small bore tubing. So it's made up of one piece of large bore tubing and one small bore tubing with your Venturi port and your mask. That makes up the Venturi setup, whether it's homemade or pre-made, okay? They're showing you here how these are different. See, when I just showed you how big the hole was, that's all they're doing. See how this one's close together, that hole would be small. This one would give you a higher FiO2 because the hole is a little bigger. And then this one's a little bigger and even bigger and even bigger. See, so you go up with the FiO2 as these jet orifices here get bigger. This is another picture of the homemade one, right? Same one we just made, except they don't have the little protection device on there. So make sure you add that little protection cup. We call it the medicine cup, but it's also there for protection, right? If I want my COPD patient to have 28%, then I better make sure I watch this port, because if it's covered up by his bed sheets, he's getting 100%. And if you ever have somebody that needs 100%, don't ever come tape the port up, okay? I'm just going to put some tape on it, and that's going to give him what he needs. Don't ever do that, because you will lose in litigation for that, okay, you will throw you up under the respiratory jail for something like that, even if he needed it. If he needs 100%, go get a non-rebreather, right? Go get a non-rebreather and put it on. Don't try to alter nothing like that, because if he dies from O2 induced hypoventilation and they come in there and there's tape on there, oh, they're gonna blame you immediately, right? You getting the blame for that. And even if the doctor says do that, and he'll say, I ain't tell you to do that, or she'll say, I ain't tell you to do that. You're like, Dr. Sonale, you did tell me, you just talk. I ain't told you nothing. If it ain't written, it ain't what? That's what we learned in the first one. If it's not written, if not charted, it didn't happen. Okay, so if you tell the doctor to change the FiO2, you say, Dr. Sonale wanted me to change, put orders in to change the FiO2 or change whatever to this device. You need to put it in the notations so that it's charted. Okay. All right, so that's the Venturi setup. All right, we got some other large flow devices, high flow devices that you didn't think about. What about the mist tint or the croupette? The one on the, that's a mist tint or a croupette. When your child has croup, right, they put them in a mist tint, also known as a croupette. It's a plastic tent large enough to enclose the whole child. Okay, here the whole baby will be in there. It has a high aerosol output device. That's why it's high flow. What if I only got 3 or 4 liters going through there? What's going to happen to that baby? What if I only have a couple of liters going through there? It's low flow. What's going to happen to the baby inside that? Huh? Yeah, it's going to be super high. It's going to suffocate. That's why you have to have that right amount of flow in there, because that's what this is, a high flow device. It's air conditioned so the baby don't get too hot, right? Primarily used to provide aerosol therapy to children with croup. Okay, croup is a disease of the lungs, and they get a cold, they get the croup cough, and it sound like that. That's the croup cough, a really harsh barking sound, and that's the epiglottis has swollen a little bit, and that's what's causing that sound. And so cool things decrease swelling, right? So we put cool mist on. Same thing as when you get extubated. We put an aerosol face mask on that patient with cool air coming through to cool off the throat, just in case, to prevent them from having stridor. Remember, because we said stridor is what you hear when the throat swell up. And it's from the door, you can remember that breath sound called stridor, right? And we have to give, you'll learn in pharmacology, we give racemic epinephrine to decrease that swelling, okay? All right, E, 12 to 15 liters per minute. So the mist tint or croupette must be at what? 12 to 15 liters per minute to prevent the buildup of carbon dioxide. It can provide approximately 40% FiO2. No smoking, of course, or sparks or spark-producing toys in that croup tent, because it can support combustion, okay? So like when I was young, we had these little cars that you could race and you do the wheels like that, and they had little sparks coming out the side, you know, like a lighter. You know how the lighter has that flint, well, the tires had that little flint on it, so when you do that, it sparks come out the back when I was younger. So you won't have the child in there like that with all that oxygen, right? Where you can get around and blow up in there. Don't let them have that, okay? Don't let them have a cap gun or nothing like that inside the doggone croup tip, okay? That's all they saying. An isolette. The isolette is another high flow device, and it's kind of like the incubator, right? Some people call it the incubator. It's a chamber designed to provide a thermally controlled, oxygen-enriched, humid environment for newborns. It's thermally controlled, right? It's warm, oxygen-rich, and humid environment for newborns, just like his mom. Okay, you're trying to mimic his mama's womb with a isolette. Okay, it's very warm. Guess who puts the baby in the isolette? Straight out of the body, respiratory. Straight out of the cooch, straight to the isolette. Especially if it's a, but you'll never forget that, right? You'll never forget that. So especially if it's a high-risk pregnancy, respiratory is in the room for all high-risk births. A C-section or any other high-risk pregnancy birth, you're in the room. Might be your turn, might be somebody else's turn, whoever's assigned to that unit for that day. So when they say, okay, we got a C-section at 12 o'clock, you need to be in there prepared, dressed out, got your isolate ready, warmed up, all of that stuff ready. So when he pop out, you put him right there. You do your APGAR score. That's when you pull on his legs and see if he responds, his color, all of that. Sucks his mouth out, make sure he's breathing, his oxygen sat, all of that immediately, right? You got to be able to do that because babies fall. When they crash fast and hard, okay? And if they have to, you put a little bitty small CPAP machine on to help blow some air in his lungs, right? You might have to be there to put some surfactant into his lungs if the lungs are tight, right? All those things when you're working in the NICU. So you be a NICU therapist with this education you got. You don't have to go get nothing new, okay, to work in the NICU. If that's what you like, then that's what you push for, okay? I want to work in the NICU. So you look for who's hiring in the NICU. Let me plug up my phone. All right, so that's the isolate. Access is provided through the side ports, right? So you ever seen that where it's got the little hole on the side where you stick your hands through there so that you're not exposing him to germs. Try to expose as less as possible. So we have little hand ports on the side, little arm ports where you can reach in there and touch him and rub his little head and adjust any kind of little monitor that you have on his body. Until you get him right. When you get him right, he's good. This patient is on a ventilator. That patient there is that sick patient there is a sick baby. He's on a ventilator. This right here is his ventilator. Okay, this is his ventilator. You see the tubing? This is vent circuit. The blue one is the inspiratory limb, and the white one is the expiratory limb, hooked up to his face, right? With a little tube down his little throat. And you're monitoring his numbers here, his rate, his volumes, his 40%, all that kind of stuff, peak pressures, all of that is being monitored on the ventilator. That's all you. That's all you. Respiratory. So that's what I tell you. You either can be a breathing treatment therapist or you can be a real therapist. See, we ain't did breathing treatment yet. You see all this stuff that we do. We put in arterial lines, all kind of stuff, right? But some people older, it's usually older female therapists that I run into that don't want to do a lot of extra stuff. They've been a therapist for 20-something years. Don't come in and talk about you want to start intubating now and doing all this kind of stuff. No, we want to just get these little treatments, eat our food, breakfast, do our little treatments, come eat our lunch together, gossip, and go home. That's what they do. I promise. I experienced it. But it's usually the young females or the young guys who want to do more. Y'all ain't doing, because some hospitals, they don't let respiratory intubate, okay? If it's a training facility that has a school built into it for anesthesiologists. The anesthesiologist, if they have anesthesia students, then they do all the intubations, right? They call you to the floor, somebody's coding, anesthesia's coming, and their students will practice because they got to do that in surgery 1,000 times a day when they're doing surgeries, right? And so, but if it's not a training facility, then respiratory is doing the intubating, okay? But you want to try to go where you can so you can keep your skills. Because if you don't never do it, then for 5-6 years and you go somewhere and they expecting you to know how to do it, then you're going to look crazy because you ain't did it in years. So don't go to a nursing home fresh out of school. Go to the med or some type of ICU, level 1 trauma, where you can see all the brains and all of the, get that out your way, right? You've seen it, dealt with it. And then you can back down because that looks good on your resume. When you got to move to another state and they see you worked at a level 1 trauma center for a couple of years or a year or something, that's going to pick you faster than somebody else that worked at a nursing home for a year. You're going to get picked, okay? All right, head box. This is the head box. Look at the little head box. This is the enclosure that fits over the head of the newborn. It's warmed, humidified, oxygen is supplied to a little box by a large bore tubing. You have a minimum flow of 7. Don't go any less than 7. If not, you're going to build up the what? CO2. All right. If it's too high of a flow, it might produce what? Noise, and the baby start crying because it's too loud. All that in his ear. So it's a good little happy medium you have to try to find. All right. But you have the little leads. I have put little monitor leads on them, monitoring his heart rate and sat. This is the oxygen here. With large bore tubing would hook up to here. Then he has a little toy hanging in there. They have a little visual stimulation so he can look at the little butterfly hanging or something like that to keep his attention. And the oxygen analyzer will be here measuring how much oxygen is inside of that head box, okay, with an oxygen analyzer. All right. Now, here go our aerosol setups, which I've already taught you. These right here. Large volume nebulizers with the Venturi principle. See how I told you they look different? See, this is a large volume nebulizer with the Venturi thing on it. See it? This is the Venturi. You see this window right here? That's the Venturi port, and you turn that blue one. You turn it left or right for the oxygen. Same thing for this yellow one here. You turn it left or right for the oxygen content. Now, I don't know why the company made this yellow. That's the craziest thing in the world, that you would make this yellow, because yellow is signified as medical gas, right? But this is for oxygen. Okay, so it's crazy. I don't know why they did that, because anybody else would think, well, let me plug this up to the yellow one, right? But no, this is for oxygen. If it's got an FiO2 on it, it's for oxygen. All right. And this is the setup here. You see how you have two large bore tubings. You got an aerosol Trach Mask here, and you've got a little T-piece thing here, and I don't know what this other stuff is, but this is an aerosol setup. The flow must be how many times the minute ventilation? 3 times. That's his demand. 3 times the minute volume is the patient's demand if you're going to have an aerosol setup. At high FiO2s, usually greater than 60, then a tandem might be necessary. Now, what did we say about needing flow or needing FiO2, right? He might not need a lot of FiO2, he just needs that flow, right? So if we got him down to like 28%, the total flow gonna be high, right? Because the lower the FiO2, the higher the flow. But what if he need the flow and oxygen? He need that flow and he needs some more oxygen in order to keep them sats up. Then what we do is then as a tandem, right? Tandem means 2, right? So we would have 2 flow meters up there, right? We have one hooked up going to the patient, then we have another line from the other one going into that one as well, okay? So there's a certain, it's called a Misty Ox. I don't have one on me now, but it's a Misty Ox one, which has hooks up to your bottle of water, right? And it goes to the oxygen flow meter, okay? You'll turn the oxygen flow meter all the way up. And then it has a little side port that a small bore tubing will hook up to another oxygen flow meter and crank that one up. So now you got double flow meters going to that one bottle. That's called a tandem, okay? If you need higher FiO2s and flow, then we can use that tandem, okay? And the way we measure the FiO2 with the tandem is with an oxygen analyzer, or we can use a formula, all right? Because the gin, the Misty Ox doesn't have Venturi on it. It's pure oxygen, okay? And what you do is you use pure oxygen sometimes, and then sometimes if I want to bleed that oxygen down, then the second port will go on what? Oxygen or air? Air. If I want to bleed it down. If I don't want to bleed it down, I need all that oxygen and more flow, then I'm going to hook it up to another oxygen port, okay? Another oxygen port. But what you need to know is the aerosol setup must be 3 times a minute ventilation, which is a demand, okay? Cannot be set up with oxygen source gas as at FiO2 less than 30%, approximately depending on manufacturer, set up on air and bleed O2 in. So this is what it's saying. If I have a aerosol setup and I have using 2 of them, okay, don't hook up to the oxygen flow meter if I need FiO2 less than 30%, right? If I need them 30% or less, I'm gonna hook it up to the air and then bleed the oxygen in. If I need higher than that, then I'm gonna hook it up to the oxygen and bleed the air in. Understand? Let me get one. If I have this set up, if I have this set up like this, guys, and this is hooked up to what? Oxygen. Now, if this didn't have a Venturi setup and there's pure oxygen coming through, but I wanted to blend it down, then this would have a little side port here, and that would hook up to an air flow meter.
That's only if it didn't have the Venturi.
If it don't have a Venturi system. If it doesn't have a Venturi system, then this is 100%, okay? So if I want to bleed that 100% down, it'll have a little side port here, right? And that little side port will hook up to an airflow meter. And then I would put my oxygen analyzer on the end right here and measure it. It'll just be like, let's say 100% on my little machine, okay? And then I would turn the air on, little bit by little. As I turn the air on, the oxygen on here, the FiO2 is gonna start dropping on my analyzer. Okay, so if the doctor said I want him on 40%, and you don't have a Venturi setup, you can use the tandem one, right? You hook it up to oxygen, and then bleed your air in, okay? And then as you turn the air up, the FiO2 is gonna start dropping. And when it drops to where you want it, you leave it there. Hook it up. That's an oxygen analyzer, okay? But that's only if you don't have the Venturi setup, okay? If I don't have a Venturi setup, I can measure it with my oxygen analyzer, okay? And it's also known as a gin or a misty ox. Let me see if I got one right quick so you can see it.
Yeah, that's what I'm saying. So you saying they don't have 2 pints, 1 medical air and 1 oxygen. You don't bleed depending on what they need.
Put the air in, but you know, mix the air with the oxygen, but you don't turn the air up more to make the oxygen in its right level.
But that's depending, right? That's what he's saying, depending on what they need. Because you could essentially turn the oxygen down and bleed the air. I mean, and I'm asking, because that's 1 for 3 rounds. Because I'm thinking he's trying to say, or what I'm getting from it is he's saying, depending on what
you have the Venturi, then that's when you have to hook it up to medical gas.
yeah, I get that part. What I'm not getting is he saying that it could potentially be more air than oxygen?
You bleeding it in together.
Yeah.
So it's mellow in it.
Yeah, but
All right, so this will be what
I got a
talking about.
question. I asked her, she could help me. Okay, so are you saying that it could potentially be, okay, I know you're saying that it's 2 tanks, right?
Here,
Basically
two
2 tanks.
walls, yeah.
Or well, 2 walls, 2 tanks, or whatever, whichever source you can the oxygen in the air, medical air from. You're saying that it could potentially be you're raising the air more than the oxygen, or the oxygen more than air, right?
Well, what I'm saying is trying to, basically, but what I'm saying is if I'm trying to, look at this one right here. Does this one have a Venturi on it?
No.
No, this doesn't have a Venturi. So this is called the GIN, gas injection nebulizer. It's gonna give pure oxygen, okay? So let's hook this one up. If I have this one, and I think this one will fit on this bottle too. If I don't have the Venturi, one, and all I have is the GIN, which does not have the Venturi orifice on it, right? It's just straight up oxygen coming out of here. So this will be on here. This goes down into the bottle, the Bernoulli Principle for this one. Screw on to here. Okay, now I have, this is 100% oxygen, right? Okay, so I'll put them up like this. All right. So that's 100% oxygen coming out of there, okay? Now, this what this one is for. This is the little side port. If I want to bleed this oxygen percentage down, then this side port will hook up to what? The air, a yellow flow meter, right? The one that's usually right next to each other on the wall. I would screw this one up to the yellow one, and I would turn the yellow one up until the FiO2 percentage goes down to what I want. Okay? Got it? Okay? That's why I would, sometimes we use these, okay? But thanks for most modern technology, they now have what's called a blender, okay? We have O2 blenders that simply have a yellow cord and a green cord on the back of it, and you put that on the flow meter, turn them on, and then there's a knob, what you want, 40%, you want 30%, whatever you cut it on, it's gonna give you the right amount of air and oxygen to the patient. You don't have to be doing all this tweaking it, right? You don't have to do all this analyzing, right? If you have a blender. But if you don't have a blender, and it's good to know without a blender how to do it if you don't have a blender, okay? Because some places might not have. You might be in Corinth, Mississippi somewhere, and they don't have a blender. They got these, right? So you just simply turn this on and then hook this one up to the airflow meter and turn the air to the point so this percentage goes down to what you order, what the doctor ordered. Right now, what's the percentage coming out of here? 100%. So if I hook this to the airflow meter and start cutting the air up, this is going to start going down. And you just keep on doing it until you get to where you want to be. If the doctor say he wants 60%, you cut the air up until it goes down to 60. If he wants 50%, you cut the air up until it goes down to 50. Okay, that's it. That's it. Very rarely will you have to deal with that. Usually you're just going to have the ones you saw on the PowerPoint. These right here, okay? And like I said, they come in different colors and shapes and sizes, but as long as they have the Venturi principle on there, that's what you would use. Cut your flow up and you're there, okay? That's what they own, either aerosol, whatever you got them on, aerosol T-piece, aerosol tray collar, aerosol face tint, or what have you, okay? That's all it is. Don't overthink it. All right? Now, if I don't have an analyzer, I do have to figure out now how much oxygen am I getting, right? How much oxygen is actually and flow is going to the patient. If I don't have an analyzer and I have two of them working at the same time, they have a formula for that, okay? But you're not going to have to memorize the formula because there's no questions about the formula. So this is the aerosol setup, which I've showed you when I showed you. All right. Now, cascades is the next high flow device. A cascade says it needs a blender of or two sources to titrate the FiO2. Most any FiO2 is attainable and most any flow is obtainable. So determination of FiO2 with any combination, this is it right here. So what I showed you, if you got two of them going, you just simply take the first FiO2 times the first flow plus the second FiO2 times the second flow and divide that by the first flow plus the second flow. And that will give you your FiO2 or your total flow of that system, those two systems. But you don't have, like I said, you don't have to do this. Now, when I say cascade, see this container right here? This is known as a cascade humidifier, okay? It's sitting on a hot plate. This thing right here is a hot plate. Okay, there's a little plate that this slides up on. It heats the water inside of here, okay? And so as the water comes, the air goes across the water, it picks up the moisture and goes to the who? To the patient, okay? Same thing as what we just showed, it's just heated, okay? Like I told you, remember I told you the aerosol, whatever, some of them have ways that you can heat them, okay? Some of them have ways that you can heat the top of it or the whole bottle of water gets heated up. Or if you don't have that and you have the cascade, but you have an actual little box humidifier that heats up, you put this little plate here, you feed water into it and it heats the water up, okay? Now you got nice hot moisture coming through here, okay? That's all that's saying. That's a cascade, all right? All right, so let's look at the high flow devices again. Number one, Venturi Mask. The second one, mist tint or croupette. The third one, isolettes, head box, aerosol setups, all of the ones that are included in those, and cascades. Okay, those are all high flow devices, not to mention your ventilators, but you don't go into ventilators in this class. Okay, those are your high flow. Now, what is the criteria for high flow device? Criteria for high flow.
More than lower, lower respiratory rate.
Not lower.
More than
respiratory rate greater than 25. The tidal volume is not 300 to 700, right? And not consistent pattern. That's the main thing. So basically, is if you don't qualify for low, then you qualify for high. The qualifications for low flow devices are consistent regulatory pattern, ventatory pattern, respiratory rates less than 25, and a tidal volume about 300 to 700. That's consistent, nice and smooth and easy, right? Those are the ones that qualify for low flow. If they don't have that, then they don't qualify for low flow. You have to put them on a high flow device, whether that's a Venturi Mask. For adults, it'd be either the Venturi Mask or your high flow aerosol this, aerosol that, aerosol this, aerosol that, okay? If it's your babies, you put them in a mist tint, croupette, head box, right? For if it was a baby, okay? And then, of course, when you get on a little further, you're gonna learn ventilators is also a high flow device, Okay. All right. Now, what's today? 11. Oh, no. The day is Wednesday. What is today? Is the do you have the syllabus? Let me look at the syllabus. Let me stop the pause and look at the syllabus right here. Hyperbaric therapy, guys, is what's next coming up. Remember, we talked about this a little bit. I touched on it, talking about going down 1 atmosphere, 2 atmospheres, or 3 atmospheres. And at sea level, the barometric pressure is 760. That's 1 atmosphere, right? That's sea level, right? And we said the pressure of oxygen at sea level is 159 millimeters of mercury, because we said 760 times 0.21, okay? Now, if we want that oxygen to do higher work and work stronger, then we can go down an atmosphere. So what if we got 2 atmospheres? What would the pressure of oxygen be at 2 atmospheres? At 2 atmospheres. 319. So look, that same room air now exerts a pressure of 319 millimeters of mercury. See how that shot up? Just by going down 1 atmosphere. So the same room air has way more benefits now at 1 more atmosphere, right? And that's the hyperbaric chamber. When we put you in a chamber, we bring the pressure down 1 atmosphere, 2 atmospheres, we can go down 3 atmospheres, okay? So that the oxygen that you do have works harder, okay? It's able to do more, okay? Because at sea level is 159. What if it's 3 atmospheres? Because most of them go down to about 3 atmospheres. So what if it's 3 atmospheres? What's the pressure of oxygen then?
478.
Huh?
478.
478? That's what you got to? Okay. So about 478. You did 760. So it's 760 times 3 times 0.21. And you got what, 468?
478.
478 millimeters of mercury at 3 atmospheres. So at sea level, it's just 159. But if we go down 3 atmospheres, we have 400, almost 480 millimeters of mercury of pressure. So that's oxygen being forced through the tissues that much better. Okay.
What do you mean by going down?
Yeah, going down.
Okay.
It looks like you're going up.
No. It's the pressure. The atmospheres. It's just like a diver. You're gonna learn when we go over hyperbaric therapy.
Oh, okay.
When the divers go down real deep, the pressure is higher.
Yeah,
And they can't come up fast. If they come up too fast, they get the bends, right? The nitrogen in their blood starts to bubble, and then it can kill you. So they have to come up slowly.
Okay.
All right. So divers that have been diving for a long time, they put them in a hyperbaric chamber to bring them back up slowly to atmospheric pressure. Okay. So hyperbaric therapy brings the pressures down. It's harder, heavier. See, it's 760 on room air, but then 2 atmospheres is 1520 of pressure. 3 atmospheres was what? 3 times 760 was? No, 3 times 760. I'm talking about the atmospheric pressure.
It was 22
Something like that, over 2,000.
Yeah.
Yeah, millimeters of mercury. See that? And so that's what I mean by atmospheres. Okay. And so that's what you do to divers when they dive deep and go like 200 feet down. They can't just come straight up. If they do, they would die. Okay, because they're decompressing too fast. You have to decompress slowly, and so they'll put them in a hyperbaric hyperbaric therapy or chamber, and bring them back up slowly, and it has their body decompress slowly. That's safe. If not, they can get the bends. It's called sickness called the bends. Okay, and that's what happens. And we'll go into that on tomorrow. I just wanted to show. So we got hyperbaric therapy. Talking about the therapy, this is the different types of hyperbaric therapy chambers. See, these are different chambers here. And then we got to do oxygen analyzers. And I think after the analyzers is over, it's done. Okay, yeah. So tomorrow we will start at hyperbaric therapy. If you want to go on and kind of be ahead and look at it, you can. But what we're doing in hyperbaric therapy is super saturating the oxygen, the blood. We're super saturating because it was 159 out here, but I can get you down to 480. That's called super saturation. And they do that for people who have perfusion problems, right? If your blood don't go down well, I can make the blood that does reach them feet way more effective than if you weren't in hyperbaric, okay?
I have a question. How many atmospheres possible to go down?
I don't know. I know it can go down to about 3 in the hyperbaric chamber.
Okay.
They go down to about 3. I don't know how far you can go down. That's safe. But you're going to learn there's different types. You got some that's for everybody. There's some that's just for one person. So that's what we're going to do on tomorrow. After this class, I'm going to stop the class today, and I'm going to put some homework in for tonight. Okay, I will put some homework in for tonight. Make sure you do that by midnight. And see you tomorrow over to finish up the lecture. Then Friday, you're going to come in. We're going to go over some of the lab, let you check off on these labs. Make sure you know how to show me a cannula. Make sure you're able to show me a simple face mask. You got to be able to show me a aerosol face mask, aerosol T-piece, aerosol trait collar, right? And set them up. I showed you some of that today. And also I have videos of the previous lab that's in the module. You have the book. There should be no reason why you can't hook this stuff up on Friday, okay? So if you don't know a large bore tubing from a small bore tubing on Friday, it's because you did not watch and you did not study, and you will not be checked off. I will send you away and you will have to make it up another day, okay? Please remember that labs are pass or fail. If you don't get all the labs done, I don't care if you got 100 average, you fail 210, okay? It's pass or fail. You have to get them done. It's mandatory before you go on to 220. That's just the way it is, and that's what it is from the get-go. It's pass or fail. If you don't do the labs, you can't go on, okay? So get these labs done. Make sure you study. In the syllabus, it tells you what pages in the lab book to look at, where I'm going to be checking you off. It tells you all the check-off pages. Look for the previous pages or chapters in the lab book, and it gives you more information about these devices, okay? And what we're looking for. It's totally on you to get this stuff handled, all right? So tomorrow we'll do hyperbaric chamber and oxygen cylinder, analyzers, right? Which measures the FiO2 of the gas. And that's gonna be it, okay? We'll show you a few more things, because that's gonna take probably most of the day, because it's a lot of information. But other than that, you will be up to you to look at the videos that are available for you in the module, do the reading and this lectures, and you should be able to hook this stuff up by just putting it on the table, and you grab what you need. If you look at it and study it, you'll be able to do it with no problem. I'm going to tell you to set one up and then tell me what the total flow of it is. I'm going to say, okay, set Mr. Johnson up on a 40% aerosol trait collar. You got to go show me an aerosol trait collar, hook it up and put it on the mannequin, right, the right way, and then go to the board and tell me what the total flow of that device is. What you just did today. Okay, what you just did today. Now, you might not can do it today, but if you study this lecture and go back and look at it, look at the PowerPoint, do your reading, you should have no problem at doing this, okay? It's totally up to you guys. It's holding y'all accountable of this information, because this is a lot of information, but if you don't look at it, you ain't gonna get it, okay? But y'all are doing well, and I'm proud of the students that are doing well, and you can continue to do well, but you gotta stay on it, all right? So I will see you guys tomorrow morning. Have a good day.